Hello friends. It's a beautiful morning wherever I am, and I hope it's a beautiful morning wherever you are. So today I would like us to wind up with temperature, ideal gases, and thermal properties by specifically looking at. We shall specifically be looking at the solutions to past paper questions. So these past paper questions of so many years are going to help us to get confidence in this unit of ideal gases, temperature, and thermodynamics, because they will act as practicing questions. And as we answer them, I am very sure we shall develop the confidence we need to answer questions in our exams. So what you're going to do is you are going to pull out your document that I told you about. This is the document. So pull out your document which has solutions to past paper questions. And here I have pulled out mine. Pull out your master kit A-level physics, that is revision questions. And you're going to scroll to page you're going to scroll to be able to scroll to page. Actually, let me check which page is. Look through the contents to see the page, the exact page where you are supposed to be. I'm trying to check the page. So temperature ideal gases is on page 400. So I'll just type here 400. 400. My keyboard is not responding very fast. I don't know why. But you just know it is page 400. So you can look for page 400. Make sure you have your document in hard copy. It is easier that way. You can't use it in soft copy. So I'm looking for page 400. I'm almost there. Okay, so this is the document. So this is page 400, yes. Page 400, temperature, ideal gases, and thermal properties. It is actually supposed to be thermodynamics, but that is fine. So let's take this opportunity to run through these questions. Now, sometimes I will give several methods of calculation, so it will be up to you to record all of them, or you can record one after all the video is recorded, the lesson is recorded. You can always refer to the lesson to see another method if you need it. Somewhere I will use several methods. If you have gone through most of your notes, if you have gone through most of your summaries, if you have followed the previous lessons, then this lesson will be very, very fruitful. It will be very helpful. This is going to be a long video because the document could be bigger, but I know you may not watch it on the same day. So let's begin with the first question. These questions are specifically quoted from past paper questions between 2021 and I think around 2006, around there. So this is a very good tool for our revision. So let us start. The first question, these questions are mixed. They are not specific that this is for temperature, this is for ideal gases, this is thermal properties. That's why I labored to teach all the three areas so that the questions are just attempted once. So number one, at a pressure of, I think I should maximize this so that I have a full. I want to have a full page. I don't know if it is possible, but that's fine. I can bear with this. So at a pressure of 1.05 times 10 power 5 and 27 degrees Celsius, 1 mole of helium gas has this volume. The mass of 1 mole is actually 4.00 grams. Calculate the root mean square speed of an atom of helium gas for a temperature of 27 degrees. So I will begin with the simplest method. I think I will begin with the simplest method. I don't know whether it is the simplest anyway. But so first of all, we know that in the list of formula, we are going to always be given an expression which can always guide us. We shall always be given an expression to guide us, such as PV is equal to 1 over 3 mn root mean square speed. That expression is always given, so we shall always be maybe referring to this expression. So we want to find the root mean square speed. We have the pressure, we have the volume, we just don't have we don't have the what? Okay, we have 1 mole, but we know that if I make this mean square speed the subject, this would give me 3 times PV divided by m times n. Remember, m is the mass of a molecule and n is the number of molecules. That means m times n is actually going to be the mass, which mass is given as 4 grams. So without hesitation, without wasting time, without even wasting any time, we shall simply substitute. So this will be 3 times 1.05 times 10 power 5 times the volume, which is 0.0240, divided by the mass. Remember, the mass of one molecule times the number of molecules will be the mass of the gas, which is given as 4 grams. So this will be 4.00 times 10 power negative 3. So we are trying to press our calculator. Let me pull out my calculator. Pull out your calculator and try to check with me. So 3 times 1.05 times, exponent 5 times 0.024 divided by open brackets 4 exponent negative 3. So this is giving me this average square speed as 1.89 times 10 power 6. 1.89 times 10 power 6, but we want the root mean square, so we find the square root both sides. So it means the root mean square, which I'll write as C root mean square, is going to be equal to the square root. So this is the square root of 1.89 times 10 power 6. And when you press your calculator, I'm pressing mine, square root. When you press the calculator, you most likely getting the same as mine, 1.37 times 10 power 3 meters per second. So that is my first method. That is my first method. I will use the second method. So I know that this answer is around 1.37 times 10 power 3. For the different methods, you may not get this exactly the same to a given number of significant figures, but to a certain number of significant figures, again, the answers will be the same. I will also use the expression for kinetic energy. We saw in our lessons that the average kinetic energy, EK, which can be the same as a half m average of c squared is also equal to 3 over 2 times kt. We saw that expression. You can always derive it. Many times we shall derive it because this is given, but we shall always use this several times to arrive this. We shall see such questions ahead. Okay, so I think this is even the easiest. This is even the easiest. I will only take this part here. I will only take that part there. Remember, K is R over NA. K is also given the list of constants, and K is 1.38 times 10 power 1.38 times 10 power negative 23. The temperature should always be in Kelvin units. That means we shall have 27 plus 300, plus 273, which gives us 300 Kelvin. So we are now substituting. Remember, half has cancelled, so it means that average square speed is going to be equal to 3 kt divided by m. When I find the square root, I will be finding the root mean square speed. So I'm substituting, just substituting. This will be 3. This will be 3 over 2 times k, which is 1.38 times 10 power negative 23. That is Boltzmann's constant. Then times the temperature, which is 300, divided by the mass. Now here, when it comes to the mass, remember this is the mass of one molecule. This m is the mass of one molecule. So if we want the mass here, this mass which was given, it was the mass of the gas, yet this m is the mass of one molecule. But remember, 1 mole of a gas has the same mass as has the same number of atoms as 6.02 times 10 power 23. So if I want the mass of one atom, then I'll simply say 4.00. This is the mass of all the atoms in the gas, divided by the number of atoms, which is 6.02 times 10 power 23. So this is the mass of one atom. And when you press your calculator, you are most likely getting almost the same, 1.87 times 10 power 6. And when you find the square root, you'll get approximately the same value of the root mean square speed as 1.37 times 10 power 7. So here you get the square root. So the root mean square speed will be the square root of 1.87 times 10 power 6. And that gives you the answer. Oh, can I use method 3? Maybe I can still use another method. But that means I will have to rub off some of these. Okay, let me try to rub off some of these. Why can't I increase the size of the rub? Okay, so let me try to use method 3. So method 3, I will simply use the ideal gas equation. PV is equal to nRT. And we have already seen that PV is also given as PV is equal to nRT. And we have also seen that PV is also equal to a third. PV is a third m n mean square speed. PV is equal to nRT, which is a third mn. So I'll take this part here. I'll take only this part. I'll take that part. So I'm now simply going to substitute. So substituting, I'll have that. Remember, we have 1 mole of the gas, so this will be 1.00 times the molar gas constant, which is given as 8.31 in the list of constants. The temperature must be in Kelvin units, that is 300. This should be equal to a third times, remember, m times n is the total mass, which is given as 4.00. Changing it to kilograms, I will say times 10 power negative 3. This gives us the the mean square speed, C. So when I try to find the mean square speed, C, pressing my calculator, you can also press yours. Okay, my calculator is giving me 1.87 times 10 power 6. When I try to find the root mean square speed, that is CRMS, this is the square root of this, which is 1.87 times 10 power 6. I am getting back approximately the same value. So that is question number 1. Let's proceed slightly. Now I'm going to find a challenge with this. Can't I shift my recording tool to somewhere else? Okay. So this is part 2. Using your answer in part 1, calculate the root mean square speed of the atom. Using your answer in part 1, calculate the root mean square speed of the atom at a temperature of 177. So the other one was at 200, was at 27, which was 300. So we have to change this. So remember, from the expression that average kinetic energy is equal to, of course, a half m average of c squared, which is the same as 3/2 times kt. All these ones are constants. This is a constant. So we can see that the mean square speed is directly proportional to the temperature. The mean square speed is directly proportional to temperature. So I will simply say that the mean square speed is equal to a constant times the temperature. So for the first case, or for the second case, whose root mean square speed we want, let's say the mean square speed in the second case, c squared, is going to be the constant times the temperature, which is 177 plus 273 to change it to Kelvin units. Then I will divide this by the first conditions. The mean square speed in the first case was approximately 1.8. Which one should I use? Let me use the first one, which was 1.89 times 10 power 6. This should also be equal to a constant times the temperature, which was 300 Kelvin. So the constant is the same, so it has cancelled out. So we just try to make mean square speed the subject. So the mean square speed is going to be equal to the temperature, what is 177 plus 273. So this will be simply 450 divided by 300 times this value here, which is 1.89 times 10 power 6. So now you are going to get the square root to find the root mean square speed. So C root mean square is going to be the square root of that. And when I press my calculator here, so pressing the calculator, I am getting 1.68 times 10 power 3. So the root mean square speed when the temperature is 177 degrees Celsius is most likely 1.68 times 10 power 3 meters per second. Okay, next, let's move to the next question. The pressure P and volume V of an ideal gas are related to the density by this expression here. Are related to the density by this expression here. State what is meant by this symbol here. I've been talking about this every time. So we start with these brackets. These are read as mean. And then it is squared. So it is mean square speed. Or average square velocity if you want. Or you can say average square velocity. The mean square speed or average square speed, the mean square speed of molecules, if I want to make it longer, that is the mean square speed of molecules. Okay. Use the expression to show that the mean kinetic energy EK of the gas is given by that expression. So which expression are we using? We are using the expression P. Because I don't have enough space, I'll just try to improvise here. So we are using the expression P equals to 1 over 3 times rho mean square speed used above. So we are going to use this expression to show that the kinetic energy is equal to that. I think this is easy. Number one, I'll use the whole of this space because there is no space given here, so you can also improvise. So first of all, we know that density is mass over volume. Density is going to be the mass over the volume. But remember, the mass of the gas is equal to the mass of one molecule times the number of molecules. So this is divided by volume. Density will be the mass, m, of mass of one molecule times the number of molecules divided by volume. So I'm going to remove density. So it means the expression now becomes that pressure is equal to a third mass of one molecule times the number of molecules divided by volume, then times the mean square speed of the molecules. So this therefore is taking me to another expression. I'm multiplying both sides by V, so it becomes PV is equal to a third m number of molecules times the mean square speed. Remember, PV can also be equal to nRT. PV is also equal to nRT. So I will just straight away equate this to nRT, where n is the number of moles. N is the number of moles, if you remember. N is the number of moles, and N, the number of moles is given as, the number of moles is given as the number of molecules divided by Avogadro's number. We saw this. Also remember that R over Avogadro's number is K. R over Avogadro's number is K. Remember that K is equal to R divided by Avogadro's number. We saw that also in one of the lessons. So I'm just going to substitute here. So I now have that a third m n mean square speed is equal to, where there is n number of moles, I'm putting there number of molecules over Avogadro's number times R times T. But where there is R over NA, I will put there K. So this means I will have that a third mass times number of molecules, average of C squared is equal to N times K times T. Okay. So n has cancelled out. I don't know that people have seen that n has cancelled out. But if it has cancelled out, then I remain with a third. I'm going to use this space here, but I will rub it when I am attempting this part. So I now have that a third m mean square speed is equal to k times t. If I multiply both sides by a half, I'm multiplying both sides by a half. So I now have a third into a half. M average of c squared, this is going to be equal to a half times kt. But a half m's average of c squared is the average kinetic energy, which has been called Ek, or the mean kinetic energy. So this means I have a third times the mean kinetic energy Ek is equal to a half times kt. So this simply implies that Ek is going to be equal to 3 over 2 times kt. This is a very easy expression. You just play around with the simple expressions and the simple concepts. Okay, let's go to part B. Let's move to part B. Moving to part B. In part B, I'm going to rub off this part because I need this part. I need this part. So, okay, let me see if I need it anyway. But I think I will need it. So I need to rub off what I've written here. But I know you have now mastered it. You can always arrive at that expression there. So an ideal gas containing 1 mole of molecules is heated at a constant volume. At a constant volume. If you remember the laws, some of the laws, Boyle's law, pressure law, Charles's law, when we say constant volume, something should be coming into your mind. So an ideal gas containing 1 mole is heated at a constant volume. That means volume is constant. If volume is constant, straight away a qualitative student will see that change in volume is 0 if volume is constant. And if volume is constant, remember the work done is given by pressure times change in volume. If change in volume is constant, then work done is equal to 0 straight away. Use the expression in A to show that the thermal energy required to raise the temperature of the gas by 1 Kelvin has a value of that. Thermal energy required to raise the temperature of the gas by 1 Kelvin, so change in temperature is 1 Kelvin, where R is the molar gas. So I want people to remember from the first law of thermodynamics, the change in internal energy was equal to Q plus work done. That means the change in internal energy was only depending on the heat supplied or the heat required, the heat which is added. I want you also to note that if this is an ideal gas, the amount of heat supplied only goes into changing the internal energy, but the change in internal energy is directly proportional or is equal to the total kinetic energy of all the molecules. The change in internal energy is equal to the total kinetic energy of all the molecules. That means the amount of heat which we need, Q, is going to be equal to, remember one molecule has kinetic energy which has been given above, which is 3 over 2 times kT. That is one molecule. But then we need the number of molecules. This will therefore be multiplied by the number of molecules which I'm calling N. And also remember, we have already seen that number of moles is equal to N over Avogadro's number. The number of moles is N over Avogadro's number. So this expression becomes, I'm going to remove N. So this expression becomes 3 over 2 times K times T times the number of moles times Avogadro's number. Also remember that that K was equal to R over Avogadro's number. That means K times Avogadro's number is R. K times Avogadro's number should be R. So that means our value of Q will become 3 over 2 times K times Avogadro's number, that becomes R, then times T. But there's an N here, so times small n. But now we are talking about 1 Kelvin and 1 mole. So when I substitute those two values, temperature is 1 Kelvin. Number of moles is 1 mole. So we notice that this simply becomes 3 over 2 times R. As simple as that. I hope you have tried to follow that. Next, we can go to the next part. Nitrogen may be assumed to be an ideal gas. The molar mass of nitrogen gas is 28 grams per mole. Use the answer in B to calculate a value for B Roman 1 to calculate a value for the specific capacity in joules per kilogram per Kelvin. So if we want to find specific capacity, then we know that the amount of heat required to raise the temperature of 1 kilogram of a substance, this is going to be equal to the mass times specific capacity times the change in temperature. But this has been given the previous part as 3 over 2 times the molar gas constant R. So I want to find the specific capacity. So this will be equal to 3 over 2 is 1.5 times R divided by the mass times the change in temperature, delta theta. So this is going to be 1.5, that was 3 over 2, remember. Molar gas constant is normally given as 8.31 divided by the mass. We have been given for 1 mole of a gas, the mass is 28 grams. So we shall change it to kilograms, that is 28 times 10 power negative 3. The change in temperature, we want a raise in temperature, a value for the specific capacity. Remember, it is the amount of heat required to raise the temperature of 1 kilogram of a substance by 1 Kelvin. So the raise in temperature should be 1 Kelvin. So this is 1 Kelvin. I don't need to put K here in my substitution. So the temperature is 1 Kelvin, 1.00 Kelvin. The change in temperature is 1.0 Kelvin. So we can now press our calculator very fast. This is very easy. Okay, I am getting to two significant figures. I am getting 450 joules per kilogram per Kelvin. You can also check. State what is meant by internal energy. State what is meant by internal energy. I think we looked at this in one of the lessons that we had. Internal energy. The sum of the random distribution of the kinetic. The sum of the random distribution of the kinetic energy and potential energy of all the molecules which make up a system. The sum of the random distribution of the kinetic energy and potential energy of all the molecules that make up the system. So normally when we talk about internal energy, we are looking at Ek plus Ep, but remember the molecules are in continuous random motion. That's why we are saying that it is the sum of the random distribution. This is very important because the molecules are in continuous random motion as verified by Brownian motion. So we can now say it is the sum of the random distribution of the kinetic energy and potential energy of all the molecules that make up the system. Okay. The basic assumption of kinetic theory of gases that leads to the conclusion that there is zero potential energy between the molecules of an ideal gas. We want that assumption, which proposes that there is zero potential energy between the molecules of an ideal gas. Remember, potential energy of the molecules depends on the forces between the molecules. So the assumption here is that their intermolecular forces are actually negligible. Intermolecular forces are negligible. And if intermolecular forces are negligible, it means the potential energy is zero. Or you could say no forces of attraction. There are no forces of attraction or repulsion. No forces of attraction or repulsion between molecules. No forces of attraction or repulsion between the molecules. Okay, so you can move to the next page. We can move to the next page. These questions are not well numbered, but I only cut out the most important questions so that you don't need to bother about that. The pressure P and volume V of an ideal gas are related by this expression. I say this expression is normally given in the list of formulas, so you don't need to worry about it. But immediately when I see this expression, I try to now figure out most of the expressions. So using that expression, they want us to determine this expression here. Use the equation to show that the mean kinetic energy of the molecules is 3/2 of a molecule is 3/2 is given by 3/2 kT. This is the same question we have just done in the previous page. You can even pause the video and try to see if you can arrive at it. However, if you can't, then I can just show you here, only that I don't have space. I don't have space, but I will create space, no problem. So one, we know that PV, me and you, we know that PV is equal to nRT, and we have already seen that N number of moles is number of molecules divided by Avogadro's number, so I will simply say that this is the same as N divided by Na, then times R times T. You and me know that R over Na is K, so I will just equate this to Nk times T, as simple as that. So I now bring PV is equal to NKT, I equate to this. When I do that, I now have that 1/3 number of molecules m times mean square speed is equal to n k times t. You and me will see that k has cancelled. I said if PV is equal to this and PV is equal to that, the two equations are equal. That's why I've equated both sides. And therefore, I multiply both sides by a half. So here I have a third. I'm multiplying by a half. So it becomes a half m average of c squared. Even the other side by a half, it becomes a half kt. When I multiply by a half, I know that this is an expression. A half m average of c squared is the expression for the mean kinetic energy. So this will be a third into Ek is equal to a half kt. So this therefore simply implies when you multiply both sides by 3, Ek is going to be equal to 3/2 times kt. You can't afford to fail such a simple question. Okay, then a cylinder contains 17 grams. A cylinder contains 17 grams of oxygen at a temperature of 12 degrees Celsius. The mass of 1 mole is 32 grams. We are looking at 1 mole. It may be assumed that oxygen behaves as an ideal gas, that is, potential energy of the molecules is zero. It's only the kinetic energy which is contributing to the internal energy. Calculate for the oxygen gas in the cylinder the mean kinetic energy of a molecule. So that one we have already the formula, we just use our formula. Okay, so let me try to scroll up again. So we are going to simply use the mean kinetic energy EK is given as the mean kinetic energy EK is given as 3 over 2 kT, where K is Stefan Boltzmann's constant. So I'm just substituting. This will be 3 over 2, where there is K, this is 1.38 times 10 power negative 23 times the temperature must be in Kelvin units. The temperature has been given as 12 degrees Celsius. So I'll say times 273 plus 12. So we press our calculator again. So my calculator is giving me 5.9 to two significant figures times 10 power negative 21 joules. So that is the mean kinetic energy. Then the number of molecules, I think that is easy. Number of molecules, we know that number of moles is equal to mass over molar mass, which is the same as number of molecules over Avogadro's number. So precisely we shall see that the number of molecules is going to be the mass divided by the molar mass times Avogadro's number. And when we substitute, the mass is given as 17. I don't need to change it to grams. The molar mass is 32 grams times the Avogadro's number is always 6.02 times 10 power 23. Then you press your calculator. This is easy. Grams has cancelled. So therefore your number of moles, the number of molecules is going to be 3.2 times 10 power 23. 0.2 times 10 power 23. Okay, so next, the total internal energy. The total internal energy. Remember, we know that this is assumed to be an ideal gas. And if it is assumed to be an ideal gas, then internal energy is going to be equal to the total kinetic energy of the molecules. I don't want to use delta U for internal energy. This would mean a change in internal energy. So let me just say internal energy equals to the internal energy will be equal to the total kinetic energy of the molecules. Remember, we have 3.2 times 10 power 23 molecules, and each molecule has a mean kinetic energy of 5.9 times 10 power negative 21. So this means total energy is going to be 3. The total energy is going to be the number of molecules, 3.2 times 10 power 23, multiplied by the mean energy of each molecule, which is 5.9 times 10 power negative 21. Press my calculator. So my calculator is giving me a 1000. Sorry about this. So my calculator is giving me 1000. What is happening? So my calculator is giving me 1900 joules. 1900 joules. You can also check. That is to two significant figures. I chose to put to two significant figures. Then next, define specific heat capacity. Remember I said specific is referred to per unit mass. Per unit mass. This is referring to 1 kilogram of a substance. So the thermal energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius or by 1 Kelvin is what we call the specific heat capacity. So the thermal energy or heat energy, required or needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius or by 1 Kelvin. Remember, a change in temperature on the Kelvin scale is the same as a change in temperature on the degree Celsius scale. So it doesn't change, it doesn't make any difference here when I say by 1 degree Celsius or by 1 Kelvin. So this is a specific heat capacity. Okay, let's proceed. A student carries out an experiment to determine the specific heat capacity of a liquid using the apparatus illustrated in the figure. I think we called this the continuous flow method. The liquid enters at a certain temperature on one side and comes out at a certain temperature on the other side. The mass of the liquid, the mass of the liquid flowing through the tube per unit time is m. So this is mass per unit, m is mass per unit time. M is mass per unit time. It's not just mass. The student changes m and adjusts p until the final temperature of the liquid leaving the tube is 25.5 degrees Celsius. The data shown in the figure 3.2 are obtained. Suggest why the student obtains data for two values of m. I explained this in class. Two values of m are going to allow for heat transfer from or to the surrounding. In other words, two values of m will allow cancelling out heat transfer or heat exchange with the surrounding. So this is to allow heat transfer to allow heat transfer to or from the surrounding. No, this is wrong English. It is to allow for heat transfer to or from the surrounding. If that English is hard to understand, just say to cancel out. To cancel out heat transfer to or from the surrounding. So that is the reason as to why we repeat the measurement for different values of m. Okay, so calculate the specific heat capacity of the liquid, show your working. So heat is supplied by a heater, so it means the amount of energy supplied is by the heater. Let me begin by a simpler method, a simpler illustration. So the amount of heat supplied Q goes into changing the temperature of the surrounding, but part of it is expected to be lost to the surrounding. Or I will simply say Q is going to be equal to MC, change in temperature, plus or minus the heat which goes to the surrounding. but Q is supplied by a heater whose power is actually given. So power times time is equal to the heat supplied or energy supplied. This will be equal to, I'll use a different m here because small m has been given as the mass per unit time. So I will use capital M to differentiate from that. So this is just mass times C delta theta plus or minus H. Now when I divide by T, everything by T. So the power is equal to, now mass over time is small m now. So this will be small letter m times C times change in temperature. Now I'll also say H over T, that is, I'll call it capital H. So this will be plus capital H for simplicity. Now let me substitute for 44.9 given in the table. So I will have two equations here because the method has been repeated for two values of m. So I'll have 44.9 being equal to the mass per unit time, which is 1.58. I need to change this from grams to kilograms. So this will be, because the specific heat capacity is required in joules per kilogram per Kelvin. So this will be times 10 power negative 3 to change it to kilograms times the specific heat capacity. This is C times the change in temperature, which is between 25.5 minus 19.5. This is plus or minus H, plus or minus H. For the second mass, we have power is 33.3, which is equal to 1.11 times 10 power negative 3 times the specific capacity times the change in temperature is the same, 25.5 minus 19.5 plus or minus H. Remember capital H was small h over T, so I have that in mind. We subtract the two equations. When I subtract the two equations, I have 44.9 minus 33.3. This will be equal to 1.58 minus 1.11 times 10 power negative 3 times the specific heat capacity. What is this difference? So this is times, because this will be just the same value, 25.5 minus 19.5. So this is times 6. Of course, when I subtract the two equations, this and this, these two cancel, H cancels. So we have, that's why I said to cancel out heat transfer to or from the surrounding. I'm putting plus or minus because the system may absorb heat from the surrounding, or it can also give heat to the surrounding. So when I press my calculator making C the subject, I'm simply making C the subject, 44.9 minus 33.3. So this is 1.6 divided by 1.58 minus 1.11 times 6. So this is divided by 2.82 times 10 power negative 3. So when I divide, I'm getting 4,100. That is to two significant figures. This liquid could be maybe water, because we know the specific capacity of water is approximately 4,200 joules per kilogram per Kelvin. Okay, let's continue. When the heating coil in B dissipates, 33.3 watts of power, the potential difference across the coil is given by this expression here. We are going to see, or you must have seen this in a unit called alternating current, for those who might have already studied it at this point. For now, I'll just do it for completeness for some people who may not have studied alternating current. The potential difference is measured in volts and the time is measured in seconds. So we are in SI units. Determine the resistance. Determine the resistance of the coil. So the general expression for alternating voltage is actually V is equal to V naught sine omega t. So it means V naught is equal to 27.0. That is the amplitude, it is the maximum voltage. Remember, alternating voltage keeps changing direction. At some point is negative, at some point it is positive. But it has a maximum, which we call a peak. And we know that, or we shall derive, those who have not yet derived, that the root mean square value of voltage is the value which is most important and is given by V naught over the square root of 2. We shall derive that in alternating current. The root mean square value of voltage is the one which is very important. It is given by V naught over the square root of 2. So if I want to find power, for example, from this expression, from the normal expression, power will be equal to V over R, V squared over R. But since this is alternating, I say the most important value is the root mean square value. So this will be V root mean squared over R. And when I substitute this expression here, the power which is normally considered to be the average power is going to be equal to V naught squared over 2R. I'm just putting this into that expression where there is V root mean square. I'm putting V naught over root of 2. When I square V naught over root of 2, it becomes V squared over 2. That's why you see it is 2R here. So now I can substitute. The power is given as 33.3. This is going to be equal to V naught, which is 27.0 squared, divided by 2 times R. So this gives me the value of R. So R will be equal to 27.0 squared divided by 33.3 times 2. And my calculator is giving me to two significant figures. It is giving me 11. If you don't understand this, when we study alternating current, you will now review this and it will be very easy. Okay, let's continue. Some gas initially at a temperature of 27.2 degrees Celsius is heated so that its temperature rises to 38.8 degrees Celsius. Calculate in Kelvin to an appropriate number of decimal places. I emphasize this in the examples I gave in class, but people were not actually paying attention to the lesson. So, appropriate number of decimal places. Here we have been given temperatures to 1 decimal place. So most likely, we must quote the temperatures to 1 decimal place as the final answer. And I told you, you have two values to choose, either 273 if the values given are whole numbers, or 273.15 if the values given are decimal places. So the temperature we are looking at is 27.2 degrees Celsius, so I will add 273.15. And when I add, this gives me 300.35, but I can't write 300.35. The appropriate number of decimal places will be 1 because the precision of the instrument was giving 1 decimal place. So this will be equal to 300.4. Then the rise in temperature, that one is easy. Change in temperature on the Kelvin scale is the same as change in temperature on degrees Celsius scale. So I'll just simply say 38.8 minus 27.2 without even adding 273. This will give me 11.6. If you want to convert temperatures to Kelvin, because the temperatures are supposed to be in Kelvin, then you have to convert both sides. So the difference in temperature will be equal to 38.8 plus 273 minus 27.2 plus 273. You'll get the same thing. 11.6 Kelvin. That's why I say the change in temperature on the Kelvin scale is the same as the change in temperature on the degree Celsius scale. Next, state the meaning of this symbol. This is the mean or average square speed of the molecules. Mean square speed of molecules, or the average square speed of molecules. I'll not waste time there, we'll just continue. Use the expression which has been given on the previous page. On the previous page, they have given us that the density rho, the pressure P, is equal to a third times rho average square speed. Using that expression, we are going to find the average kinetic energy to be 3/2 kT. I think we have already done that. This is, when you repeat something many times, it becomes interesting but boring. So, to begin with, here we have density. I will have to remove density. I know that density is going to be the total mass of the gas divided by the volume. The mass of the gas is equal to the mass of one molecule times the number of molecules divided by the volume. And we know that N will be equal to the number of atoms of the gas, or number of molecules of the gas. Number of atoms of the gas, because they said explain any symbol you use. Number of atoms of the gas. So therefore, this equation, pressure equals to a third rho, will now become pressure will be equal to a third. Where there is rho, I will put mn divided by v. I think I need to explain v also. V is the volume of the gas. Okay, times mean square speed. So P is equal to that times mean square speed. And of course, when I multiply both sides, it becomes PV. So PV is equal to a third mn mean square speed. But also remember, PV is equal to nRT. PV is equal to nRT. And N, number of moles, is number of molecules, capital N, divided by Avogadro's number R. So this would be N over Na times RT, Avogadro's number Na. Remember, R over Na is Stefan Boltzmann's constant K. So this will be equal to N times K times T. N times K times T. So I have PV is equal to NKT. Now I'm just going to equate this equation here to this equation here, because they are equal. So it means I will simply say that a third mn mean square speed is equal to n times k times t, and kn has cancelled out. I'm going to multiply both sides by a half. So I have a third into a half m mean of c squared. The other side also by a half kt. Note that a half m mean squared, that will be kinetic energy, mean kinetic energy. So therefore I have that a third times the mean kinetic energy Ek is equal to a half times Kt. So simply we are saying Ek is equal to 3/2 times Kt. You can't afford to fail such a simple question. You cannot. Okay, let's continue. Let's continue. We don't have time. Helium-4 may be assumed to behave as an ideal gas. A cylinder has a constant volume of 7.08 times 10, so this is the volume, 7.8 times 10 power 3, and contains helium-4 gas at a pressure of this. This is the pressure, and the temperature is given as that. Calculate for the helium gas, the amount of the gas. That's what you call the number of moles. So from PV is equal to nRT, without wasting time, the number of moles is going to be equal to PV over RT. So substituting, number of mole, pressure is 2.1 times 10 power 7. Volume is 7.8 times 10 power 3, changing from centimeters cubed to meters cubed, I will say times 10 power negative 6. Divide by molar gas constant is normally quoted in the list of constants as 8.31. The temperature must be in Kelvin units, 290. Press calculator. This is easy. Press the calculator very fast. Okay. So from my calculator, this is giving me 68 moles. Then the mean kinetic energy of the atoms. We have already got the formula above there, that the mean kinetic energy or the average kinetic energy EK was equal to 3 over 2 times KT. When we substitute, this would be 3 over 2. K is Stefan Boltzmann's constant, which is R over Na, or the molar gas constant over Avogadro's number, which gives us 1.38 times 10 power negative 23. I think it is always quoted, the list of constants, so times 290. Press the calculator very fast and check. So my calculator is giving me 6.0 times 10 power negative 21 joules. 6.0 times 10 power negative 21 joules, that is to two significant figures. Avoid writing an answer which is less than two significant figures unless it is exact. However, sometimes when it is an estimate, when they tell you to estimate, that one you can write one significant figure because it will be an estimate, especially when it comes to the interatomic spacing or the size of an atom. They tell you to estimate the volume of an atom or the volume of the gas. An estimate can be given one significant figure, but any other answer which is not exact should not be to less than two significant figures, unless when you press the calculator it gives you exactly that value without rounding off. Next, the total kinetic energy. We have the mean kinetic energy of the atoms. We have the mole, number of moles, and we want the total kinetic energy. So total kinetic energy, this will be equal to the kinetic energy of all the molecules. The total total internal energy, not total kinetic energy. Internal energy or total internal energy. The total internal energy will be equal to the kinetic energy of all the molecules. And this is very simple. We have the mean kinetic energy of the atoms, and each atom has a mean kinetic energy of 6.0 times 10 power negative 21. All we need is the number of these atoms. Number of atoms, remember, is given by number of moles times Avogadro's number, because number of moles is number of atoms divided by Avogadro's number. So this is going to be number of moles times Na. So total kinetic energy or total internal energy is going to be equal to the mean kinetic energy of one atom, which is 6.0 times 10 power negative 21. Number of moles, we have obtained it as 68 times Avogadro's number, which is quoted as 6.02 times 10 power 23. Press the calculator. When I press my calculator, okay, so this is giving me to three significant figures will be enough. This is 2.46 times 10 power 5. 2.46 times 10 power 5. Okay, next I will go to number next. without wasting any time. The thermistor of the resistance of a thermistor at 0 degrees Celsius, that is ice point, is that at steam point is 190. We know that the resistance is decreasing as temperature increases. So assume that the resistance of the thermistor varies linearly with the temperature. That is just an assumption which may not always be true. And this is the reason as to why the centigrade scales may not always give the same reading, or they may always vary. Capture the temperature of the water. We want to capture the temperature of the water when the resistance is 2300. I will use a simple sketch because we have assumed the resistance varies linearly. So if I sketch a graph of resistance against temperature, it should be a straight line. And it is varying linearly, it is actually decreasing. At 0 degrees Celsius, the resistance has been given as 3840 ohms. That is at 0 degrees Celsius. Then at 100 degrees Celsius, let's say this is 100 degrees Celsius, somewhere here. At 100 degrees Celsius, the resistance has been given as 190 ohms. Then a resistance of 2300 must be between these two values. So a resistance, I think I need to change a color here, is the understanding. So a resistance of 2300 ohms must be somewhere in between here. So the temperature should also be in between here. This is the temperature we want. I will call this one theta. Because it's a straight line, the gradient is going to be constant. I prefer to use gradients for simpler understanding. Rather than quoting a formula, I would prefer to use gradients. So gradients 840 minus 190 divided by the change in the x-axis, which we are starting from 0 minus 100, should be the same as when I take 2300 minus 190 still divided by the change in the x. I've started with 2300, so that should be theta minus 100. So we now have only one unknown. So I'm making theta the subject. I'm making theta the subject. To some people this is hard. Let me just first simplify this so that people can see. So I have 3840 minus 190 divide by negative 100, because 0 minus 100 is negative 100. So divide by negative 100. So this on the left, I have negative 36.5. So on the right, I have 2300 minus 190. So this is 2110 divided by theta minus 100. Cross multiply. When we cross multiply, it hurts me to cross multiply. I would just say theta minus, okay, that is not going to be seen. Theta minus 100 is equal to 2110 divided by negative 36.5. So this is going to be 2110 divided by negative 36.5. So this gives me negative 57.8. Now I take 100, this minus 100, the other side, I simply add plus 100. This is giving me 42.2 degrees Celsius. So whatever method you use, I think this is the easiest. This is the easiest. This is the easiest. I just look at the gradient. So that is, the temperature should be 42.2 degrees Celsius. Okay, let's continue. The temperature of the water as assumed on thermodynamic scale is actually 286 Kelvin. The temperature of the water as measured on the thermodynamic scale is 286 Kelvin. By reference to what is meant by thermodynamic scale of temperature, comment on your answer in Roman 1. By reference to what is meant by thermodynamic scale of temperature, comment on your answer in Roman 1. So first of all, there are two ways of thinking about this. They say the temperature as measured on the thermodynamic scale is this. And this is approximately when you subtract 273. So you have 286 minus 273 to change it to degrees Celsius. This is 13 degrees Celsius. So first of all, we shall say 286 Kelvin is equivalent to 13 degrees Celsius. And the thermodynamic scale does not depend on the property of a substance. So change in the resistance of the thermistor with temperature cannot be linear as it is assumed to be. You notice that on the thermodynamic scale, 286 is equivalent to 13 degrees Celsius and not 42.2 degrees Celsius. 286 Kelvin is equivalent to 13 degrees Celsius and not 42.2 degrees Celsius. What does that mean? So the thermodynamic scale does not depend on the property of a substance. The thermodynamic scale does not depend on the property of a substance, so the change in resistance of the thermistor with temperature is not linear as assumed. If it was linear as assumed, then the thermodynamic scale would give us 42.2 degrees Celsius. But the thermodynamic scale is giving us an equivalent of 13 degrees Celsius. Alternatively, you would do it the other way and say 42 degrees Celsius, you convert it to Kelvin. If you check 42 degrees Celsius and see if it is 286, if you check 42.2 degrees Celsius, this would be when I add to 73, this becomes around 315 point, I think 0.2. But because it's 1 degree Celsius, I mean to two decimal places, I would add plus 273.15. So this becomes approximately 3 Kelvin, which is not the same as 286. So still the reason remains the same. The thermodynamic scale does not depend on the property of a substance. So the change in resistance of the thermistor with the temperature is not linear as assumed. Okay, let's just continue. A polystyrene cup contains a mass of 95 grams of water at 28 degrees Celsius. A cube of ice of mass 12 grams is put, so ice is of mass 12 grams is put in the water. Initially, the ice is at 0 degrees Celsius. The water of specific capacity. This is stirred until the ice melts. Of course, stirring is to attain thermal equilibrium. Assuming that the cup has negligible mass and that there is no heat exchange with the atmosphere, calculate the final temperature of the water. The specific latent heat of fusion of ice is this. Now, I want us to note what is happening here. The water is at a higher temperature of 28 degrees Celsius. So the water will lose heat. But where will this heat go? Part of this heat will melt the ice. When all the ice has melted, its temperature now rises to the final temperature of the mixture. That means the heat lost by the water, part of it goes into melting the ice, and part of it raises the temperature of the melted ice. So I'll simply say that the heat lost by the water, is this space enough? I will improvise. The heat lost by water goes into melting the ice. So that was heat that melts the ice, and part of it is the heat that raises the temperature. Because after melting, melting occurs at no change in temperature. After melting, now the temperature rises to the final temperature of the mixture. So this is going to be plus the heat that raises. What is to raise? Is it Ri? The temperature of the melted ice. Remember, for change in temperature, it should be mass, specific capacity times change in temperature. For melting, it is just mass times latent of fusion. I will not write these formulas again because I want to substitute. If there is change in temperature, that heat is mass times specific capacity times change in temperature. If there is no change in temperature, then that heat is mass times latent of fusion, since this is ice. So for water, the mass is 95 grams. So I'll say 95 times 10 power negative 3 times the specific capacity of water is 4.2 times 10 power 3. There is a change in temperature. The temperature of the water falls from 28 to a final temperature, which I will call theta. So this change in temperature is 28 minus theta. That is the heat lost by the water. In melting the ice, we use this formula here, mass times latent of fusion. The mass of the ice is 12 grams. So this would be 12. This would be 12 times 10 power negative 3 times the latent heat of fusion of ice, which has been given as 3.3 times 10 power 5. I can't put change in temperature when ice is melting. But after the ice has melted, again, the temperature of the melted ice must rise to the final temperature, theta. So theta is above the temperature of ice, which is 0 degrees Celsius. So this will be now the mass of the ice which has melted, that is 12 times 10 power negative 3 times. Now I'm using the previous, when there is a change in temperature, I use the one above. Specific capacity of ice. Specific capacity of ice. Remember, melted ice is also water. So the specific capacity is going to be the same as the specific capacity of the water. So this will be times 4.2 times 10 power 3. Then the change in the temperature of the melted ice must rise from 0 to the final temperature, theta. So the change in temperature will be theta minus 0, because theta is higher than the initial temperature of melted ice. So I can't say 0 minus theta. Instead, I will say theta minus 0. So we now have to solve this simple equation. Let me press my calculator. You should also press yours and verify. 95 exponent negative 3 times 4.8 exponent 3. So this is 3. I'm just trying to make this one look simpler. 399 into 28 minus theta. Then 12 exponent negative 3 times 3.3 exponent 5. So this is equal to 3,916 plus, of course, this 0 is useless, so I'll have 12 exponent negative 3 times 4.2 exponent 3. So this is plus 50.4 theta. So open the brackets here, 399 times 28. So I'm just going to collect like terms. I'm multiplying this, I also subtract this, so I'll say minus the product minus 3960. So this side I have 7212. I'll take 399 theta the other side, it will be plus. So it will be 50.4 theta plus 399 theta. So I will just say divide by open brackets 50.4 plus 399. I'm getting 16.05. So this means my value of theta is 16.05 degrees Celsius, or approximately 16. So that is the value. All you need to note is conservation of energy is very important. When the water loses the heat, part of it melts the ice. And when all the ice has melted, its temperature now starts rising until it reaches the final temperature of the mixture. So that's why I have heat that melts the ice plus heat that raises the temperature of melted ice. When ice has melted, it is now water, so the specific capacity is the same as that of water. I hope I've tried my level best to explain that. Let's continue. State Avogadro's number. Avogadro's number, I think that is an easy question. Avogadro's number, that is simply the number of atoms of carbon-12, number of atoms the number of atoms of carbon-12, or the number of atoms in 0.012 kilograms of carbon-12. So I will simply say the number of atoms in 12 grams, or 0.012 kilograms of carbon-12. That is Avogadro's number. The number of atoms in 0.012 kilograms of carbon-12, or the number of atoms in 12 grams of carbon-12. That is Avogadro's number. Remember, it is 6.02. That is 6.02 times 10 power 23 atoms. Next, a balloon is filled with helium gas at a pressure of this and a temperature of 25 degrees Celsius. The balloon has a volume of that. Helium may be assumed to be an ideal gas. That is, its internal energy will simply be the kinetic energy of the molecules. Determine the number of gas atoms in the balloon. So that is very easy. The ideal gas equation, PV is equal to nRT, which is equal to the number of particles divided by Avogadro's number times R times T. Because number of moles is N over Na. So I can even use the expression from here. So I'm now substituting because I want number of gas atoms, that is capital N. So number of gas atoms will be equal to P times V times Avogadro's number divided by R times T. Substitute pressure 1.1 times 10 power 5. Volume 6.5 times 10 power 4 times, changing it from centimeters cubed to meters cubed, that would be 10 power negative 6. Divide by, times Avogadro's number, 6.02 times 10 power 23. Divide by molar gas constant, 8.31. Temperature in Kelvin, that is 225 plus 273, which gives you 298 Kelvin. Press the calculator. So this is giving me 1.7 times 10 power 24 as the number of gas atoms. You can check also. Next, state what is meant by the mole. Of course, the mole is just a unit of the amount of substance, those who remember. So the mole must be the amount of substance. So the mole is the amount of substance which contains as many elementary entities or particles as there are in 12 grams of carbon 12. So I can simply say is the amount of substance containing the same number of particles, atoms, molecules, the same number of particles as in 0.012 kilograms of carbon 12. I can say a mole is the amount of substance containing 6.02 times 10 power 23 atoms. As simple as that. Because I know the number of atoms in 0.012 kilograms of carbon 12 is 6.02 times 10 power 23 atoms. So sometimes I will change the definition to that. The amount of substance containing the same number of particles as there are in, let me add here something, as there are in 0.012 kilograms of carbon 12. And in this 0.012 kilograms of carbon 12, we have 6.02 times 10 power 23 particles. So I could simply say a mole is the amount of substance containing 6.02 times 10 power 23 atoms or particles. Okay, that is the mole. Next, let's scroll and continue. Next part. So they have given us two containers A and B joined by a tube of negligible volume. The containers are filled with an ideal gas at a pressure of that. So the pressure of the gas is this. The gas in A has this occupies that volume at that temperature. The gas in B occupies this volume at this temperature. Calculate the total amount of gas, that is number of moles. So I'll find the number of moles in A and number of moles in B. So I'll just simply add. So number of moles is from PV is equal to nRT. Number of moles, so let me write here PV is equal to nRT. So total number of moles will be PV over RT. I will simply add because I add the number of moles in A and the number of moles in B. So let me begin with A. In A, I have pressure 2.3 times 10 power 5 pascals. Volume is 3.1 times 10 power 3, changing it to meters cubed to be times 10 power negative 6. Divide by molar gas constant 8.31 times the temperature in Kelvin units. This temperature is 290 and this temperature is 303. So this will be times 290. This is the number of moles in A. So I will say plus the number of moles in B. Pressure is 2.3 times 10 power 5. Volume is 4.6 times 10 power 3 times 10 power negative 6. Divide by molar gas constant 8.31 times the temperature, which is 303. Now we add, get the total amount of the gas. Okay, so I am obtaining 0.716 to three significant figures. You can also verify yours. You can verify. Next, So that is the total amount. You see there are so many marks here which are simply wasted. Just adding that, you get 4 marks. So this next question, the kinetic theory, sorry, the kinetic theory of gases is based on some simplifying assumptions. The molecules of the gas are assumed to behave as hard, elastic, identical spheres. That is one of the assumptions. State the assumption about ideal gas molecules based on the nature of their movement. Nature of their movement, we know that the molecules are in continuous random motion. That one is very easy. Random what? Random motion. The molecules are in continuous random motion, or we can say they have a constant velocity until they hit the walls or they collide with other molecules. But to be specific, to be simpler, I will simply say continuous random motion. The molecules are in continuous random motion. Then about the assumption which is about their volume. We know that total volume of all the molecules, because they are very small, if we were to find their total volume and compare with the volume of the whole container, then the total volume of all the molecules, the total volume of molecules, total volume of molecules is negligible. Total volume of molecules is negligible compared to the volume of the containing vessel. So when if you get the total volume of all the molecules, you will notice that it will be very, very small compared to the volume of the vessel which is containing the gas. This is simply because the radius or the diameter of a molecule is negligible compared to the average intermolecular distance. So I can write this also in a different way and say the radius or diameter. So I can say that the radius or the diameter of a molecule is negligible compared to the average intermolecular spacing. Compared to the average intermolecular spacing. The radius or diameter of a molecule is negligible compared to the average intermolecular spacing. So that means the total volume of molecules is negligible compared to the volume of the containing vessel. Although the gas fills up the whole container, the volume of the molecules themselves is very, very small. Okay, next. So here we have a cube. We have seen this cube while dealing with ideal gases. A cube of volume V contains n molecules of an ideal gas. Each molecule has a component Cx of velocity normal to one side S of the cube, as shown in the figure. The pressure P of the gas due to the component Cx velocity is given by the expression this. So the pressure is given by that expression, where m is the mass of a molecule. Explain how the expression leads to the relation. So we want to explain how does this expression here lead to this relation here, where This is the mean square speed of the molecules. That is the mean square speed of the molecules. So we have 3 marks to explain how we can move from this expression here to this expression here. So, number 1, we are now explaining. First of all, we are going to notice that a molecule has a component of velocity in 3 directions, in 3 dimensions. Therefore, we need to consider the components in all directions. So, a molecule, so I'm saying that a molecule has components of velocity in 3 directions. In 3 directions. So the resultant, I will call it c squared, is going to be equal to cx squared plus cy squared plus cz squared. That will be the resultant in the 3 directions. But then remember, we have a large number of molecules moving randomly, and for random motion we take the averages. So I'm saying for random motion, because there is a large number of molecules moving randomly, for random motion we take averages. For random motion we take average. So taking the average, then we shall say that average of c squared is equal to average of cx squared plus average of cy squared plus average of cz squared. But remember, since they move randomly, then the averages are actually going to be approximately the same. So we know that average of cx squared is approximately the same as average of cy squared, which is approximately the same as average of c in the z direction squared. What does that imply? So it implies, or we are trying to say that average of c squared is approximately the same as 3 times average in one direction, let's say cx squared. I've only considered in the x. So, why isn't my handwriting good? So now we have that average of c squared is going to be equal to 3 times average of c squared in the x. So this therefore means PV is going to be equal to n m, where there is cx squared, we are going to replace it with average c squared, and then this will be divided by 3, divide both sides by 3. So this will be times a third average of c squared. So we have now arrived at the expression PV is equal to a third n m average of c squared as required. Now this explanation is what is very important here. These two and this part is the most important, are the most important things here. A molecule has components of velocity in 3 dimensions, so in 3 directions. So the resultant in 3 directions is given by that. Then for random motion, we take averages. We take the averages. So we take the averages, and taking the average, yet the averages are approximately equal to each other. Then this gives us the 3 that you see in that equation. Okay, next. The molecules of an ideal gas have a root mean square speed of 520 meters per second. Root mean square speed 520 meters per second at temperature of 27 degrees Celsius. Temperature is 27 degrees Celsius. Calculate the root mean square speed of the molecules at a temperature of 100 degrees Celsius. Calculate the root mean square speed of the molecules at a temperature of 100 degrees Celsius. If you remember very well, we have already seen that kinetic energy, average kinetic energy, which we know as being equal to a half m mean square speed is going to be or is equal to 3 over 2 times kt. We now know that. So we know if a half m is a constant, 3 over 2 times k are constants, then we know that the mean square speed is directly proportional to the temperature. So I will simply say that the mean square speed is equal to a constant times the temperature. So the molecules of an ideal gas have root mean square speed at this temperature. The temperature must be in Kelvin units. Changing 27, this gives us 300 and I think that is 300 Kelvin. Changing 100, that is 373 Kelvin. So now I'm just going to consider two equations. When I use the first condition and when I use the second condition, I will start with the second condition because I want to find for the second condition. So the mean square speed is going to be equal to a constant times the temperature, which is 373. I will divide this by the second condition. The mean square speed here they gave us the root mean square speed, so I can square it. So I will have 520 squared is equal to, because I'm dividing, I may not put the equal signs here. So this will also be a constant times the temperature here is 300. So I'm trying to find the mean square speed when the temperature is 100. So we can now just get 373 divided by 300 times 520 squared. Then we shall find the square root because we need the root mean square speed. So you will notice that C root mean square is going to be 520 times the square root of 373 divided by 300. So I've got the square root of 520, of course. So I just say 373 divided by 300 square root, then times 520. I'm getting 579. So this is 579.8. 579.8, and when you write this to around two significant figures, that is approximately 580 meters per second. So that is the answer to that question. Next. Again, we are defining specific heat capacity. Specific, remember I said it is per unit mass. The quantity of heat energy required or needed to change, this is latent, not heat, not specific capacity. Specific is per unit mass. Latent means hidden, concealed. We can't see the physical effect of applying the heat. So here, latent, when we see latent, we know that is change of state. Specific is 1 kilogram. So that quantity of heat required to change the state of a unit mass of a substance without a change in temperature is what we call the specific latent heat. So the quantity of heat or thermal energy required or needed to convert or to change the state, to change the state of a unit mass. When I talk about unit mass, I'm referring to 1 kilogram of a substance the quantity of heat energy needed to change the state of a unit mass of a substance without any change in temperature. Without any change in temperature is what we call the specific latent heat of that substance. Okay, next. The heater in an electric kettle has a power. The power is given as that. When the water in the kettle is boiling at a steady rate, the mass of the water evaporated in 2 minutes times 2 minutes is 106 grams. The specific latent heat of vaporization is 2260 joules per gram. Note it is joules per gram. Calculate the rate. Calculate the rate of loss of thermal energy to the surroundings of the kettle during the process. So let's first of all look at the energy that has been supplied. The energy supplied, I'll call it ES, energy supplied, is of course power times time. And power times time, the power is given as 2400, I guess, times the time is 2 minutes times 2 minutes, that is 2 times 60. And when I press my calculator, this is 288,000 joules. Then which energy is required to vaporize the liquid? Energy required to vaporize, how will you call it? EV. Energy required to vaporize the liquid. Energy required to vaporize the liquid. You can even write it in full. Energy required to vaporize the liquid. Remember, this is given by mass times latent heat of vaporization. So this will be equal to, and the mass which is vaporized, the mass which is to be vaporized is 106 grams. So I'll multiply, because this is in joules per gram, I may not change from grams. Let me just say this is in grams times the latent heat of vaporization, which is 2260 joules per gram. I've not changed these units because I know per gram and grams will cancel out. And this is giving me 226 times 106. So this is giving me 240,000 joules. That is the energy which is required to vaporize. So where does the rest go? Maybe it is the one which is lost to the surrounding. So the difference or the loss, energy which is lost, what is supplied is this and what is used to vaporize is that. So this is 288,000 minus 240,000. When you subtract, you get 48. Is it 48? Let me see. 288 minus 240. That's 48. So we have 48,000 joules. That is the loss, but we want the rate of loss. That means it is the loss over time. So the rate of loss is going to be equal to 48,000 divided by the time, which is 120 seconds. When you press your calculator, I think 48 by 12, that is 4. So this is giving me 400 watts. So the rate of loss is 400 watts. Okay, next. State what is meant by an ideal gas. State what is meant by an ideal gas. Ideal gas. So we said for an ideal gas, it should be obeying the equation PV is equal to nRT at all values of pressure, volume, and temperature, where P is the pressure of the gas, V is the volume of the gas, and T is the absolute temperature. Remember, N and R are constants, where N is the number of moles and R is the molar gas constant. So to get these three marks, an ideal gas is a gas which obeys which obeys the equation PV equals to nRT. PV is equal to nRT at all values of P, V, and T, where P is the pressure of the gas, V is the volume of the gas, T is the absolute temperature. It is the thermodynamic temperature, not any temperature. T is the absolute temperature. N is the number of moles of the gas, and R is the molar gas constant. So by saying that it is a gas which obeys the equation PV is equal to nRT at all values of pressure, volume, and temperature, those are 2 marks. So you have to define all the quantities in that expression to get all the 3 marks. Okay, next. 2 cylinders A and B are connected by a tube of negligible volume as shown in the figure. So you have cylinder A and cylinder B, the volumes are given. Volume is different, pressure is different, most likely the temperature will also be different. So let's see what the question requires of us. So initially, tap T is closed. The cylinders contain an ideal gas at different pressures. Cylinder A has a constant volume of that and contains the gas at that pressure and temperature that. Show that the cylinder A contains that number of moles, that is easy. Number of moles is equal to PV over R times T. We simply substitute. The pressure is 3.4 times 10 power 5. The volume is 2.5 times 10 power 3 times 10 power negative 6 to change it to meters cubed. Divide by the molar gas constant, which is 8.31 times the temperature, which is 300. Press your calculator. 3.4 exponent 5 times 2.5 exponent negative 3 divided by 8.31 times 300. Of course, the temperature is in Kelvin. So this is giving me a 0.341, which is of course approximately 0.34 to 2 significant figures. Cylinder B has a constant volume of this and contains that number of moles of the gas. When tap T is opened, the pressure of the gas in both cylinders becomes 3.9 times 10 power 5 pascals. No thermal energy enters or leaves the system, so we normally call such a system adiabatic. No thermal energy enters or leaves the gas. Determine the final temperature of the gas. Determine the final temperature of the gas. Now the gas is mixing. That means the gas at higher pressure is doing work on the gas at lower pressure as the gas mixes. So we shall need the total amount of the gas in the 2 containers. And the total amount of the gas in the 2 containers will help us to find the final temperature. So total amount of the gas in the 2 containers can be obtained by adding simply the number of moles. We can simply add the number of moles. And then using the formula PV is equal to nRT, we can still find the final temperature. So total amount of the gas, total amount is going to be equal to 0.34 plus 0.20, which is going to be equal to 0.54 moles. Total amount of the gas. Now I'm going to use the formula PV is equal to nRT. Note that the pressure has changed and the pressure is different, and of course the volume will be called the total volume, and then the temperature will be the final temperature. So using PV is equal to nRT, pressure is going to be 3.9 times 10 power 5 pascals. The total volume will be the first volume and this one, so that will be 2.5 plus 1.6 times 10 power 3, changing to meters cubed, that is 10 power negative 3. Negative 6, changing to meters cubed. So this will be equal to, the number of moles is going to be 0.54. That is the number of moles. Molar gas constant is actually 8.31, then times the final temperature T. This is an easy expression. You just press the calculator. 3.9 exponent 5 times 2.5 plus 1.6 times 1 exponent negative 3. Then I divide by 0.54 times 8.31. So I'm getting T as 356.3 Kelvin. Two significant figures, this is around 360 Kelvin. You can also verify. So that is the final temperature of the gas. You see that the final temperature is higher than the temperature of cylinder A. By reference to work done and change in internal energy suggests why the temperature of the gas in cylinder A has changed. Notice that the new temperature is 360 Kelvin. The initial temperature of cylinder A was 300 Kelvin. So why is the temperature different then? It has changed from 300 Kelvin to 360 Kelvin. So because the other gas in cylinder B was at a high pressure than the gas in cylinder A, then it means the gas passed from cylinder B to cylinder A. So it implies that the gas was doing work on cylinder A. That work would cause a change in internal energy, which would cause a change in the temperature. So we can simply say that the gas in cylinder A, gas passed from, let's say gas passed from cylinder B, from cylinder B to cylinder A. Gas passed from cylinder B to cylinder A, implying that work is done on the gas in cylinder A. So work is done. Work is done on the gas in cylinder A. Work is done on gas in cylinder A by the gas from cylinder B. And since no heat enters or leaves the system, the work becomes an increase in internal energy. No heat enters or leaves. So internal energy increases and hence the temperature increases. So internal energy internal energy, and hence temperature. Increase. Because temperature is the average kinetic energy of the molecules, internal energy is because internal energy will be the total kinetic energy of the molecules since it is an ideal gas. When total kinetic energy of the molecules increases because work is done on the molecules in cylinder A, it means the internal energy has increased. And when the total kinetic energy increases, even the average kinetic energy increases. So the temperature will therefore increase. Okay, let's continue. So we have here an ideal gas in a cylinder is, an ideal gas in a cylinder is 1.8 times 10 power negative 3 meters cubed, and the pressure is that at a temperature of 297 as shown in the figure. Okay, let's see the first part of the question. The thermal energy required to raise the temperature by 1 Kelvin, change in temperature by 1 Kelvin of 1 mole is 12.5 joules. The gas is heated at a constant volume. That means there is no work done because work done depends on the change in volume, such that the internal energy of the gas increases by 95.0 joules. Calculate the amount of gas in mole in the cylinder. So now finding moles, number of moles is PV over R times T. Simple substitution. The volume is 1.80 times 10 power negative 3 times, that is the pressure times, no, this is the volume. The pressure is, what is the volume? Did I get it right? The volume is 1.8 times 10 power negative 3. The pressure is 2.6 times 10 power 5. So I'll say times 2.60 times 10 power 5 divided by the molar gas constant, which is 8.31 times the temperature in Kelvin is given as 297. You press your calculator. The calculator is giving me to two significant figures 0.19 moles as the number of moles. Okay. The rise in temperature. We want the rise in temperature. Excuse me. So the rise in temperature, we can find, let's find the rise in temperature. Okay, so we know that the amount of heat supplied, if there is a rise in temperature, the amount of heat supplied delta Q, the change in the amount of heat supplied will be equal to the mass specific capacity times the change in temperature. So the amount, they have told us that the gas is heated at a constant volume such that the internal energy of the gas increases by 95.0 joules. Note that internal energy, change in internal energy is equal to Q plus W. But since the volume is constant, W is equal to 0. So it means the change in internal energy is equal to Q. So that means the change in internal energy will be equal to the amount of heat supplied, or the change in the heat, or the amount of heat supplied, which is now going to be 95.0. This would be equal to the mass. The mass is given, I think they gave us the mass. What was the mass? We have got the amount of the gas. So this let this be the number of moles, which is 0.190. Actually, I will not use mass since this is an ideal gas. I'll wrap this to be N, and I'll make this one to be CV, meaning at a constant volume. So this is going to be 0.190 times the molar gas, the specific capacity, molar heat capacity at constant volume, which was given as 12.5 joules. That is the amount of heat which was required to change the temperature by 1 Kelvin of 1 mole. So this would be 12.5 joules per Kelvin per mole, then times the change in temperature. When you try to find a change in temperature by dividing both sides, change in temperature, 95 divided by 0.19 times 12.5. So this gives you 40 Kelvin. So the answer here is most probably 40 Kelvin. Um, part part two, part two. Use your answer in part one. Use your answer in part two to show that the final pressure of the gas in the cylinder is actually this. We want to show that the final pressure of the gas in the cylinder. Remember, the volume was constant. If the volume is constant, pressure is directly proportional to temperature. So I'll just say P1 over T1 should be equal to P2 over T2. We want the final pressure. Final pressure. So it means the final pressure P2 will be equal to T2 over T1 times P1. I just made P2 the subject. So when I substitute the temperature, remember 40 is the temperature rise. It is not the temperature. It is the temperature rise. So temperature T2 is going to be 297 initial temperature plus the temperature rise, that is 40, divided by initial temperature, which is 297, then times the pressure, initial pressure, which is 2.60 times 10 power 5. Then we press our calculator. 297 plus 40 divided by 297 times 2.6 exponent 5. So this is giving me 2.950, which is 2.95 times 10 power 5 pascals. Okay, part B. Part B. Part B. The gas is now allowed to expand. No thermal energy enters or leaves the gas, so it is adiabatic. The gas does 120 joules of work. So Q is 0 because no thermal energy is entering or leaving. But the gas does. So the work done is going to be negative 120 because we said when the gas expands, the work done is negative. Work done by the gas is negative. So state and explain whether the final temperature of the gas is above or below. So change in internal energy, the change in internal energy is going to be equal to Q plus W. Because Q is 0, the change in internal energy is going to be negative 120 joules. So it means the change in internal energy is also negative, which means a decrease. A decrease in internal energy means a decrease in the kinetic energy of the molecules, which means a decrease in the average kinetic energy of the molecules, which means a decrease in temperature. So we are saying the change in internal energy, the change in internal energy, the change in internal energy is equal to negative 120 joules. Negative 120 joules, which means internal energy decreases. Internal energy decreases because you can see it is negative. Then energy decreases, you see it is negative, meaning total kinetic energy of molecules decreases. Which means the average kinetic energy decreases. So the temperature is going to decrease. So they said, so the temperature, state and explain whether the final temperature of the gas is above or below 297 Kelvin. So the temperature is below. We have seen why the temperature will be lower. So that is a simple account or explanation which will give you all the marks you need for such equation. Next, again, we have state what is meant by Avogadro constant. We say this is the number of atoms in 12 grams of carbon 12. Number of atoms in 12 grams or 0.012 kilograms. 12 grams of a number of atoms in 12 grams of carbon 12. Number of atoms in 12 grams of carbon 12. That is Avogadro's constant, and this is 6.02 times 10 power 23 atoms. Part B, argon 40 may be assumed to be an ideal gas. Argon 40 may be assumed to be an ideal gas. A mass of 3.2 grams of argon 40 has a volume of 210. So this mass, argon 40, has 210 centimeters cubed at temperature of 37 degrees Celsius. Determine for this mass of argon 40 the amount in mole. The amount in mole, that is the number of moles. So that is easy. Number of moles is given by mass over molar mass. The mass is, what is the mass? Is 3.2. I think it is 3.2 grams. The molar mass is 40 grams. You just look at argon 40. So when you divide, this is very easy. I think this gives you 0.080. I'm trying to maintain two significant figures. So 0.080 mole. Then the pressure. Remember, PV is equal to nRT. So pressure P is going to be nRT divided by the volume. Make sure the temperature is in Kelvin. So the number of moles, 0.080 times 8.31 for the molar gas constant. Temperature 37, I think 37 is 310 Kelvin. So that would be 310 divided by the volume is 210 centimeters cubed. It will be 210 times 10 power negative 6 to change it to meters cubed. Press the calculator. So this is giving me 9.8 times 10 power 5 pascals. 9.8 times 10 power 5 pascals. Okay, then we want the root mean square speed of an argon atom. There are many methods now. You should be familiar with most of them. The root mean square speed of an argon atom. You may choose to use a PV is equal to nRT, or you may just use PV is equal to a third n m, the mean square speed, because I say this is always given. But remember, n is also number of moles times Avogadro's number. Remember that. And the mass of an atom, you can get it from the mass. It is argon 40. So if it is an atom, the mass of an atom is approximately the same as the mass of a nucleus in U. So this will mean that the mass of an atom can be approximately 40 U, which will be 40 times 1.66 times 10 power negative 27 to change it to kilograms. So that will be the mass of an atom. Okay, now we can substitute. In this formula, I can now substitute very precisely. Pressure is 9.8 times 10 power 5. The volume is 210 times 10 power negative 6. This should be equal to a third times number of molecules, which is number of moles, that is 0.080 times Avogadro's number, which is 6.02 times 10 power 23, then times the mass, which is 40U, that is 40 times 1.66 times 10 power negative 27, then times the mean square speed. When you try to find your calculator and finding the mean square speed, this is something long, but it is easy. 3 times that, I just divide by the brackets, 6.02. You can press your calculator and verify my answer, which I'm trying to get. So the mean square speed that I'm getting is approximately 1.93 times 10 power 5. Then when I try to find the square root, C root mean square is the square root of this value. Okay, so this is giving approximately 440 to two significant figures. You can also verify as the root mean square speed. Next, the volume of 1 kilogram of water at 100 degrees Celsius is given as that. The volume of 1 kilogram of water at 100 degrees Celsius, water vapor at 100 degrees Celsius, and atmospheric pressure is that. Show that the work done against the atmosphere when 1 kilogram of liquid water becomes water vapor is given by that. So, first we just need to find the work done. Work done is equal to pressure times change in volume. Pressure times change in volume, let's just substitute. So the pressure is given as 1.01 times 10 power 5. And the volume change in volume is going to be, we are moving from, the other one is what? I can also say that the change in volume is, the volume of, the change in volume is very small. So this could be, okay? Or the volume of atmospheric pressure is far, far greater than the volume of liquid water. Therefore, I can just take this to be almost the same as the volume of atmospheric pressure, or at atmospheric pressure, because the volume of the water vapor is far greater than the volume of the water in the liquid state. So I will say 1.69 minus 1.0 times 10 power negative 3, but you see times 10 power negative 3 is very small. So I could even have said the liquid volume is far, far smaller than the vapor volume. So even if I subtract, I get almost the same thing. But anyway, you can try to press your calculator and see what you get. So I am getting 1.706 times 10 power 5. Of course, this is approximate 1.71 times 10 power 5 as required. The first law of thermodynamics is given by that. The first law of thermodynamics may be given by that expression. State what is meant by plus Q. We say this is heat added to the system or energy, thermal energy transfer to the system. So this will be thermal energy transfer. Specifically is to the system. Heat energy added to, you can say added to the system, that is plus Q. Then when it is plus W, we say this is work done on. Work done on the system. That's work done on the system. So we can continue. The specific heat of vaporization of water at 100 degrees Celsius is 2.26 times 10 power 6 joules per kilogram. A mass of 1.0 kilogram of liquid water becomes water vapor at 100 degrees Celsius. Mass of 1 kilogram of liquid water becomes water vapor at 100 degrees Celsius. Determine using your answer in A the increase in internal energy of the mass of the water. So we are saying that the change in internal energy is equal to Q plus the work done. And they have told us in part A, we have seen that the work done against. So the work done was negative. But then they're saying the specific latent heat of vaporization of water is this. That means 1 kilogram of water needs 2.26 times 10 power 6 joules to vaporize. So that means the change in internal energy is going to be 2.26 times 10 power 6 joules because we are looking at 1 kilogram plus the work done, remember it will be negative 1.71 times 10 power 5 because it is done against the atmosphere, so it is expanding, so the work done is negative. When you press your calculator, this gives you so this is giving you 2.09 times 10 power 6. So this is, of course, three significant figures because they said only they didn't specify the number of significant figures, but it's better to three significant figures. So this is 2.09 times 10 power 6 joules. Next. A constant mass of an ideal gas has a volume of 3.4 times 49 times 10 power 3 centimeters cubed at a temperature of 21.0 degrees Celsius. When the gas is heated, 565 joules of thermal energy causes it to expand to this volume. So there is an expansion. At 53 there's an expansion at 53.0 degrees Celsius. That is the new temperature. Show that the initial and final pressures of the gas are equal. If they are equal, that is, volume should be directly proportional to temperature. That means the pressure should be constant. Let's verify. So V1 over T1 is going to be equal to V1 is 3.49 times 10 power, I think I will change this, but even if I don't change, there's no problem. Times 10 power 3 divided by temperature. Of course, the temperature, there is no option. I have to change because this is addition, the other one was multiplication. So this would be 273 plus 21, which is 294. And this gives me 11.9. That is centimeters cubed per Kelvin. Then we go to the second one. I will say V2 over T2. This will be 3.87 times 10 power 3 divided by the temperature, 53 plus 273, that is 326. Pressing the calculator, to one decimal place is 11.9. So I can simply say that since V1 over T1 is equal to V2 over T2, which is now going to be a constant, then here we simply say pressure is constant. Pressure is the constant. So the pressure is the constant. So what is kept constant here? Okay, let's continue. The pressure of the gas is given as that. The pressure of the gas is given as that. Calculate the work done. That is very easy. Work done is equal to pressure times change in volume. So the pressure has been given as 4.20 times 10 power 5 pascals. The change in volume, the volume changes from 3.49 to 3.87. So I'll say 3.87 minus 3.49. This was times 10 power 3 in centimeters cubed. Now this time I have to change to meters cubed times 10 power negative 6. Then I press the calculator. So this is giving me out to two significant figures, 160 joules. So this is work done by the gas because it's expanding. In my mind, I know this work done is going to be a negative value. The work done by the gas is going to be negative value because it causes a decrease in internal energy. Use the first law of thermodynamics and your answer in Roman 1 to determine the change in internal energy. So the change in internal energy is equal to the heating of the system, which is Q, plus the work done on the system, which is W. So the heating of the system, they say it is 565 joules are transferred to the system. So this is positive. It is 565 plus the work done by the system. So the work done is negative. So I'll say plus negative 160. And when I add 565 minus 160, I get 405 joules. So this is the change in internal energy is 405 joules. Note that this is a positive value for change in internal energy, so it means an increase in internal energy. And an increase, a positive value shows means an increase in internal energy. Okay. Explain why the change in kinetic energy of the molecules of this ideal gas is equal to the change in internal energy. So one, we know that internal energy, I'll start from here. Internal energy is equal to the sum of the kinetic and the potential energies of all the molecules. But for an ideal gas, we know that there are no intermolecular forces, so the potential energy component is 0. There are no intermolecular forces, so no potential energy. That means the change in kinetic energy. So I will just say hence the change in internal energy, the change in internal energy only depends on the change in kinetic energy of the molecules. So by saying internal energy is the sum of the randomness of the potential energy and the kinetic energy of all molecules, you get a mark. You tell us that for an ideal gas, there are no intermolecular forces, so there is no potential energy. That is the second one. Hence, the change in internal energy only depends on the change in kinetic energy. So a change in internal energy is just equal to the change in kinetic energy of the molecules. Okay, next. A microwave cooker uses electromagnetic waves of frequency 2450 megahertz. The microwaves warm the food in the cooker by causing water molecules in the food to oscillate with a large amplitude. At this point, you will now notice that this is resonance. Say the name of the phenomenon. That is automatically resonance. The system absorbs maximum energy from the driver and vibrates with the maximum amplitude when its natural frequency is equal to the driving frequency. That was resonance. Calculate a value for the specific heat capacity. They say the effective microwave power of the cooker is that the temperature of the mass of 280 raises from 25 to 98. The time is 2 minutes. Calculate the value of the specific heat capacity. I think that is very easy. We want the answer in joules per kilogram per Kelvin. So the amount of heat supplied is equal to mc times change in temperature because it goes into raising the temperature. But the energy supplied is given by the power times time. So power times time is mc times change in temperature. So I want C. C will be equal to the power times T divided by a mass times change in temperature. I'm now substituting. The power is given as 750. The time is 2 minutes. I have changed it to seconds. That is 2 times 60 divided by the mass, which is 0.28 from grams to kilograms. And the change in temperature is going to be from 98 minus 25. 98 minus 25. So I press my calculator. Note that a change in temperature on the Kelvin scale is the same as a change in temperature on the degrees Celsius scale. So it doesn't need me to convert from degrees Celsius to Kelvin. And when I press my calculator, I'm getting so my calculator gives me 4400 to two significant figures. 4400. These are free marks. Okay, next. The value of the specific capacity determined from the data above is greater than the accepted value. The value we have is greater than the accepted value. That means we are actually using more heat to raise the temperature of 1 kilogram of a substance than it would be. A student gives us the reason for the difference that heat is lost to the surroundings. Suggest in more detail than that given by the student a possible reason for this difference. So this student just suggests that the heat is lost to the surrounding and that is all. But they're saying suggest in a more detail than that given by the student a possible reason for the difference. So you will notice that some energy may go into heating the container of the water. So as some energy is going into heating the container, it means more energy will now be required to raise the temperature of 1 kilogram of the substance. So we are saying some energy goes into heating the container itself, because the temperature of the water will not of the liquid will not increase, or the temperature of the as the temperature of the water increases, even the container will be warming up. So some energy goes into heating the container. Some energy goes into heating the container of water. But there could also be some leakage of microwaves from the cooker. This could not be, this energy could not be, or could be wasted. It could be not accounted for. It could not be going into raising the temperature of the water. So there could be, I'm saying another one could be, there could be some microwave leakage from the cooker. There could be some microwave leakage from the cooker. So it means the energy of the microwaves which leak from the cooker cannot be used to raise the temperature of the water. Okay, next. State what is meant by internal energy. By this point, you are now familiar with this. The sum of the random distribution of the potential energy and the kinetic energy of all the molecules, particles, or atoms which make up the system. So this is the sum of the random distribution, the sum of the random distribution of potential energy and kinetic energy of all molecules, call them atoms, call them particles, which make up the system. So that is internal energy. Okay, next, the variation with volume V of the pressure P of an ideal gas as it undergoes a cycle ABCA of changes is shown in the figure below. So let's see this. So we are moving from A to B. First of all, you see that A to B, the volume, it is a vertical line, the volume is constant. The change in volume here is 0. Change in volume is 0, so the work done is going to be 0. Then you see from B to C, there is a change in volume, there's an increase in volume, and there is a decrease in pressure. So there should be also a change in temperature. But it could also be possible that the temperature could also be constant, but we shall see. From C to A, we notice that the volume is decreasing. So here the work done is most likely going to be positive because it is a compression. The work done will be a positive value because the volume is decreasing. Okay, so let's continue. The temperature of the gas at A is 290 Kelvin. The temperature at B is 870 Kelvin. Determine the amount in mole of the gas. So we can use either A, we can use B. Whatever you want, you will get the same answer. So let me use A. At A, the number of moles is going to be equal to the pressure times volume over R times T. I just use PV is equal to nRT. When I substitute the pressure at A is 1 point, just read it from here. I think this is 1.2 using the scale. So that is 1.2 times 10 power 5. Then the volume at A is 4.0 times 10 power negative 3. Divide by molar gas constant is 8.31. The temperature is given as 290. So when you press your calculator, I think you get this one very easily. So this is giving me to two significant figures to 0.20. Then the temperature of the gas at C. Because now I have the number of moles, it means it's now easy. You can by the way use at B to find the same number of moles. So the number of moles of the gas will be the same. So I can now find the temperature at C, making T the subject. T is going to be equal to PV divided by NR. I'm now substituting. At C, the pressure is the same, 1.2 times 10 power 5. At C, the volume is, what is this volume? I think it is it is 7 point something. It is in the center. It is somewhere here in the center of this square. It is here in the center of the square. So this is 1, 2, 3, 4, 5, 6. This is 7.7. It is the center, so it is 7.75. So that is 7.75. So I will say times 7.75. You can verify on your graph. Divide by the number of moles. The number of moles, which is 0.20 times the molar gas constant, 8.31. Pressing the calculator. So when I press the calculator, I'm getting 560 to two significant figures. 560. You can also verify. Explain why the change from C to A involves external work and the change in internal energy. The change from C to A involves external work. If you go back to the graph, you see from C to A there is a decrease in the volume. That means work is done on the system. From C to A, you see there is a decrease in the volume. The volume decreases at a constant pressure, so work is done on the gas. Then you notice that the temperature at C, we have calculated it as 560. The temperature at A is 290. So there's a decrease in temperature, meaning that the average kinetic energy has decreased, which means that the total kinetic energy has decreased. So the temperature has decreased. So they're saying explain why the change from C to A involves external work and a change in internal energy. So one, we are saying volume decreases. Volume decreases. Volume decreases at a constant pressure. So work is done on the gas. Work is done on the gas. Work is done on the gas. That's one. But also, we notice that the temperature decreases. Temperature decreases. Temperature decreases from 560 Kelvin to 290. I think it's 290 Kelvin. Temperature decreases from 560 Kelvin to 290 Kelvin. So that means there's a decrease in the total average kinetic energy of molecules. So there's a decrease in total kinetic energy of molecules, so internal energy decreases. So internal energy, so the internal energy decreases. So the internal energy decreases. Okay, next. Define specific latent heat. Define specific latent heat. So that amount of heat, of course, specific, that is per unit mass. Latent means a hidden, concealed. So we don't see a physical change. Therefore, this is at constant temperature. So the amount of heat energy required to change the state of a unit mass of a substance without any change in temperature is what we call the specific latent heat. So the amount of heat energy or thermal energy, the amount of heat energy or thermal energy required to change the state, or the phase. This could be the phase, the state or the phase of a unit mass, That is, when I say unit mass, I'm referring to 1 kilogram. A unit mass of a substance, without any change in temperature. So that is the specific latent heat. That amount of heat energy required to change the state or the phase of a unit mass of a substance without any change in temperature. That is what we are calling the specific latent heat. Okay, part B. In part B, we have a simple experiment which we saw in one of the lessons. An electric heater is immersed in some melting ice that is contained in a funnel shown in the figure. So we see melting ice, we see a heater and water, which is as a result of melting the ice. The heater is switched on, and when the ice is melting at a constant rate, the mass m of ice melted in 5.0 minutes is noted, together with the power P of the heater. The power P of the heater is then increased. A new reading for the mass m of ice melted in 5.0 minutes is recorded when the ice is melting at a constant rate. So here they told to complete the table. The data for the power P and the mass m are shown. Let's see the question down here. The question says complete the figure to determine the mass melted per second. Mass per second, that is easy. The mass melted per second. So we have this 78 per second to be 78 divided by 5 means, which is 5 times 60. And this gives you, so this is 0.26. Then for 114, that is 114 divided by 5 times 60. So this is 0.38. So that is the mass melted per second. That's the mass melted per second. Then complete the figure. We have finished. Use the data in the completed figure to determine a value for the specific latent heat of fusion. So you can refer to your data and see. You can look at the figure. We are going to determine a value for the specific latent heat of fusion. So since ice is melting, most likely the temperature of ice is below the temperature of the surrounding. So I expect that ice is most likely going to absorb heat from the surrounding. Therefore, the heat supplied to melt the ice plus what is absorbed from the surrounding, I'm using capital H, will be equal to the capital M, which is the mass of the ice melted, times the latent heat of fusion. So the heat supplied is given by power times time plus the amount of heat which is absorbed from the surrounding will be equal to capital M times latent state of fusion. I'm using capital H for heat supply because in the question they have given us in the next part we have small h, which is the rate. That is with respect to time. When I divide by T, by T, by T, now I have power plus small h, that is rate, is equal to capital M over T is small m. That is also mass melted per second. So that is, I'm now going to have two equations. I want you to note that capital H over T is equivalent to small h. So I'm now going to have two equations. Number one, using the first power, which is 70 plus h, is going to be equal to mass melted per second, which is 0.26 times the latent heat of fusion. Using the second power, which is 110 plus h, is equal to the mass melted, which is 0.38 times the latent heat of fusion. Subtracting the two equations, 110 minus 70 is going to be equal to 0.38 minus 0.26 times the latent heat of fusion. When I make L the subject, my answer is making L dividing two significant figures. This is 330. So the latent heat of fusion is 330. Note that I've not changed from grams to kilograms because I knew the unit is in joules per gram. That's why I didn't change from grams per second to kilograms. Then the rate H of thermal energy gained by the ice. So we just solve for H. So using the first equation, I will say 70 plus H is equal to 0.26 times 330, or you may use a more exact value here and verify. So I'm just subtracting 70, 0.26 times 330 minus 70. So I'm getting 15.8. 15.8. You could be getting approximately 16 or 15 or 17 depending on what value you recorded here. So approximately 16. Okay, next, I think I should have a short break here. Let me have a short break. Okay, so let's resume. Let's continue. I wanted this video to be just one video, but it must be long, almost over 10 hours. Okay, so we're going to the next question. We're going to the next question. In a sample of gas at room temperature, 5 atoms have the following speeds. So they've given us 5 atoms with those speeds. I hope I'm on the right page. So 5 atoms have those speeds. 5 for the 5 atoms, calculate to 3 significant figures. 3 significant figures. Normally we don't note what the examiner wants. This time the examiner wants strictly 3 significant figures. The mean speed or the average speed. So the mean speed, we just sum up the speeds and square. And divide by 1, 2, 3, 4, 5. There are 5 speeds. So I will simply say 1.232 plus 1.50 plus 1.46 plus 1.28 plus 1.64. I'll multiply, of course this is times 10 power 3 because the power is the same, power of 10 is the same. Then divide this by 5. When I divide this by 5, so this is giving me 1.44 times 10 power 3 meters per second. Then in the second part, we have the mean square speed. Mean square speed. So we can't find the mean square speed the same way we have find the mean speed, not at all. This is mean of the squares. Mean square speed. So I have to square the speed. So this time I can't multiply the power of 10 this side. However, I can multiply by the power of the power of 10 to be 10 power, I think 6. It can work, but still I will just square each of them. So this will be 1.32 times 10 power 3. This is squared plus 1.50 times 10 power 3, which is also squared, plus 1.46 times 10 power 3, which is also squared, plus 1.28 times 10 power 3, which should also be squared, plus 1.64 times 10 power 3, which should also be squared. Then I divide this by 5. Then you press the calculator. 3 significant figures, remember. Okay, my calculation is giving me 2.09 times 10 power 6 to 3 significant figures. Then we find the root mean square speed. C root mean square speed is going to be the square root of the mean square speed. That is the square root of 2.09 times 10 power 6. And when you press your calculator, just square root of that. To 3 significant figures, I'm getting 1.45 times 10 power 3 meters per second. So that is the root mean square speed. So that was an easy question, I guess. Define again specific latent heat. These questions are appearing many times to make ourselves confident with them. So specific, that is per unit mass. Latent, hidden, so that is change of state without change in temperature. So the quantity of heat or the amount of heat, the quantity or amount of heat, energy, the amount of heat, energy needed or required to change, the state, or call it the phase of a unit mass of a unit mass. I said specific means unit mass. That is one what? That is 1 kilogram of unit mass of a substance. Unit mass of a substance without change in temperature or at a constant temperature. So this is without change of temperature. So that is the specific latent heat. There is a change of state without a change in temperature. In our next part, we have a beaker containing a liquid is placed on a balance as shown. The heater of power 110 is immersed in the liquid. The heater is switched on, and when the liquid is boiling, balance readings M are taken at corresponding times T. A graph of the variation with the time t of the balance readings m is shown. So they have shown us a graph of m with the time. Okay, we have seen that graph. You can look at it again. State the feature of the figure which suggests that the liquid is boiling at a steady rate, at a constant rate. Which feature of the graph will show that the liquid is boiling at a steady rate? That is a straight line. A straight line is indicating a constant gradient, therefore a steady rate, boiling at a steady rate. So the feature is a straight line. The feature we can see is a straight line. So a straight line indicates constant gradient. A straight line indicates constant gradient, thus showing a steady rate. So the liquid is boiling at a steady rate. Okay, next. Use data from the figure 3.2 to determine a value for the specific latent heat of vaporization. So use data from the figure to determine the specific latent heat of vaporization. So I will go back to the page so that I use the data from the figure. So since we have m against time, and we know that the energy supplied Q, let me call that energy supplied Q, is equal to the mass, or which is power times time, is going to be the mass times the latent heat of vaporization. If I make m the subject, you notice that now m is equal to P over L times T. So we have plotted the graph of m against T, compare with the y is equal to mx plus C. So you notice that the gradient is going to be P divided by L. So all we need is to find the gradient. Let's try to find the gradient. I will take values such as at 6. I'm taking this value here. On the x-axis, I think it is this one. On the x-axis, it is this value here. I think this is 332. Then on the other one I can take, I don't want to take this, but I can still take this one maybe. You can take this one. So the scale here is 2, 1, 2, 3, 4. I think that is 8. So this is 338, I think, 338. If I take this point here, 338. No, 368, not 338, 368. If the scale on the vertical is 2, so that is 368 here. And this on the x-axis, it is 4. 1, 2, it is actually 3. And the scale on the x-axis is 2 divided by 10, 0.2. So this is 1, 2, 3, 0.6. Yes, that is 0.6. So let me try to find a gradient. So I will say the gradient is 368 minus 332 divided by, on the x-axis I have 0.6 minus, that is minus what? 0.6 minus 6. Yeah, 0.6 minus 6. Of course, the gradient is going to be negative. That is, the gradient is negative. So this will be equal to the power, which power is 2 divided by 10, 0.2123, 0.6. Then, of course, this mass change in mass will be times 10 power negative 3, and this change in time should be times 60 because it is given in minutes, so that is times 60. The power is 110 divided by L. So let's try to press the calculator and see. 368 minus 33. Hope this is 332. 1, 2, 3, 4, 5, 6. Yeah, 332. So that is 36. 36 divide by, open the brackets. So this is 0.6 minus 6 times 60. Then I say L is going to be equal to 110 divided by that. 110 divided by the answer. So this is giving me L as 990,000, or L as 9.9 times 10 power 345 power 5. I've just ignored the negative because I was interested in only the gradient. Okay, so that is exactly the calculation for this part here. Maybe I can try to repeat it again here, just for completeness. Use the data to determine the value for the specific latent heat of vaporization. So I say the heat which is supplied is equal to the power times time which goes into vaporizing the liquid, assuming the heat losses of the surrounding are negligible. So I said we have seen when make M the subject, M is equal to P over L times the times T. We have on the x-axis we have T, on the y-axis we have T, so we say the gradient is going to be equal to P over L. So we try to find the gradient. We said we had 338 minus 332 divided by the time was from 0.6 to 6. This was in grams, so we multiplied by 10 power negative 3. This was in minutes, so we multiply this by 60 to change it to what? To seconds. And this is equal to P, which is given as 110 divided by L. When I calculated, I got L as 9.9 times 10 power, 9.90 times 10 power 5 joules per kilogram. Alternatively, you would just substitute, you would use a simple alternative method. So the power times time, I'm just going to use substitute in this expression here. Power times time will be equal to the change in the mass times latent heat of vaporization. The power is 110 times the time. I'm going to use the time for the time from t equals to 0 to t equals to 7, because the last point I'm seeing there is 7 on the graph. So this is 7 minutes, changing it to 2 seconds. The change in mass in that 7 minutes is from 372, I think that's 372 up to 325. You can look at the graph. 372 up to 325 from the graph. Some people may be wondering where. So this value here is 372, and the value here in the middle is in the middle of this box. That is 325. You can verify the middle of this box here. That is 325. So if that is true, if that is then true, I'm just substituting the expression power times time is equal to change in the mass times that into vaporization. So this is change in mass, but I have to multiply this by 10 power negative 3 to change it to kilograms. Then I multiply this by the latent heat of vaporization. And when you try to find the answer there, pressing the calculator, so L is 46200 divided by, this is difference in mass. So this is 47 times 10 power negative 3, which is giving me a value of L as 9.83 times 10 power 5. So this will also be acceptable. That will be also acceptable. State with a reason whether the value determined in 2 is likely to be an overestimate or an underestimate of the normally accepted value of the specific latent heat of vaporization of the liquid. Of course, as the liquid is vaporizing, some of the liquid could condense on the sides of the container. Some energy is of course going to be lost to the surrounding. All these ones are going to make the value that we have calculated an overestimate. If there was no loss to the surrounding, then we would require less amount of energy to cause vaporization. So we are saying some energy or heat is lost to the surrounding, some heat, some energy is lost to the surrounding. Some energy is lost to the surrounding, so this is so the value is an overestimate. Or I could even look at the vapor which condenses on the sides of the container. So as vapor condenses on the sides of the container, again, it means the energy used is more. Vapor condenses on the sides of the container. So still, the value is an overestimate. So the value is still an overestimate, because if there was no condensing, that all the vapor just leaves the liquid, then less energy would be required to vaporize what is remaining. So the value is an overestimate. Okay, so I think I should first pause from this point. Okay, so let's pick up, let's continue with our lesson. Yeah, I stopped on state with a reason whether the value determined in 2 is likely to be an overestimate or an underestimate of the normal accepted value of the specific latent of vaporization. And we said some energy is lost to the surroundings. So the value we have calculated could be an overestimate, is actually greater than the normal. Also, vapor condenses on the sides of the container, so still it means the value we have obtained is actually higher than normal, so it's an overestimate. Okay, let's continue. In an ideal gas, in an ideal gas, in an ideal gas, or an ideal gas is assumed to consist of atoms or molecules that behave as hard, identical spheres that are in continuous motion and undergo elastic collisions. State two further assumptions of the kinetic theory. So they have told us about the nature hard identical spheres. I can't talk about hard elastic spheres. The undergo elastic collisions. They're in continuous motion, so I can't talk about random. They are in continuous motion, but we can say that this motion is random, so it means I can still say, even though they are said to be in continuous motion, the motion has not been specified to be random. So another assumption could be the motion is actually random, so I can say random motion. Okay, random. How am I writing? So the molecules, we can talk about random motion. Random motion of molecules. Okay, number two. We also say the total volume of molecules themselves is negligible compared to the volume of the containing vessel. So total volume of molecules negligible compared to the volume of the container. I'll say volume of the containing vessel. So that is assumption number two. Assumption number three, we can also say the one which relates to the forces, no intermolecular forces between the molecules, no intermolecular forces except during collisions. So we assume that there are no intermolecular forces except during collisions. By the way, we can also talk about the duration of collisions being negligible compared to the time between collisions. So the duration of collisions is negligible. Compared to the time between collisions. So what do I mean by this? The time spent during collision of one another, the time of contact during collision is far smaller compared to the time between collision, that is between one collision and the next collision. That's why we say the duration of collisions is negligible compared to the time between collisions. I think those are four. Of course, there are others. There could be another one about the number of molecules. So there is a large number of molecules, so that an average behavior is always considered. Where can I write that one? There's a large number of molecules, so that an average behavior is always considered. Let me write it on. There is a large number. There is a large number of molecules, so that an average behavior is always considered. So that an average behavior is always considered. So these are just for our revision purposes, but the question wanted us to state only two. There is a large number of molecules, so that an average behavior is always considered. So those are some of the assumptions. So you can't fail to state only two. Okay, next. The next question. Helium-4 may be assumed to be an ideal gas. Show that the mass of one atom of helium is given as that. I think this is also very easy. Show that the mass of one atom is given by that. So we know that mass over molar mass is the same as the number of atoms over Avogadro's number, which is the number of atoms in 12 grams of carbon-12. So we want the mass of one atom. That means N is 1. So this therefore implies that the mass we are going to find is N, which is 1 atom, divided by the number of Avogadro's number, which is 6.02 times 10 power 23, 10 times the molar mass. The molar mass this is helium-4, so the molar mass is 4 grams. So this will be 4 times G. 4 grams, not 4 times G. And when I press my calculator, 1 divided by 6.02 times 10 power 23. So I'm getting 6.6 times 10 power negative 24 grams as required. The mean kinetic energy EK is given by that expression. Calculate the root mean square. Calculate the root mean square speed of a helium nucleus. So that one is very easy. The mean kinetic energy EK is the same as a half m, the mean square speed, which is equal to 3/2 times kt. So I just take this part here. So it means the mean square speed is going to be equal to 3 kt divided by the mass m. So this will be equal to 3 times k, which is 1.38 times 10 power negative 23 times 300 divided by m, which is 6.6 times 10 power negative 24. This was in grams, remember, so I have to change it to kilograms times 10 power negative 3. So when you press your calculator, most likely, let me press mine. Okay, when I press my calculator, I get 1.88 times 10 power 6. This is, of course, meters squared per second squared, but I want the root mean square, so I find the square root. So C root mean square is going to be equal to the square root of 1.88 times 10 power 6. Square root. The square root is giving me approximately 1.4 times 10 power 3 meters per second to 2 significant figures. Okay, next. Again, this question is back. State what is meant by the Avogadro's number. We say this is the number of atoms contained in 12 grams of carbon-12. The number of atoms in 12 grams of carbon-12. Number of atoms in 12 grams of carbon-12. Number of atoms in 12 grams of carbon-12. Then define the mole. Remember, the mole is the unit of amount of substance. The amount of substance which contains the same number of particles as there are in 12 grams of carbon-12. And remember, in 12 grams of carbon-12, there are 6.02 times 10 power 23 atoms. So I can just simply say that a mole is the amount of substance containing 6.02 times 10 power 23 atoms, particles, molecules, nuclei, etc. Or we can say amount of substance which contains the same number of particles as there are atoms in 12 grams of carbon-12. Amount of substance, sorry, it is here. Amount of substance which contains the same number of atoms, same number of particles as there are atoms in 12 grams of carbon-12. So that is the mole. Let's just proceed. A container has a volume of 1.8 times 10 power 4 centimeters cubed. The ideal gas in the container has this pressure and it is at this temperature. Of course, this temperature, changing it to Kelvin, that is plus 17. I think this is 290 Kelvin. Show that the amount of gas in the cylinder is 150 moles. So we need to find the number of moles. And number of moles is equal to PV over R times T. Simple substitution. Pressure is 2.0 times 10 power 7. Then the volume is 1.8 times 10 power 4. But is in centimeters cubed, so we change to meters cubed times 10 power negative 6. Divide by R is 8.31. And the temperature is 290. So press our calculator. So pressing my calculator, I'm getting 149. Of course, this is approximately 150 mole. Okay, next. Gas molecules leak from the container in B at a constant rate of this. The temperature remains 290 Kelvin. In a time t, the amount of the gas in the container is found to be reduced by 5%. So the amount has been reduced by 5%. So what remains is actually 0.95%. So the question is, calculate the pressure of the gas after that time. So remember, what remains is 95%. What has been reduced is by 5%. Therefore, I will simply use the same formula. PV is equal to nRT. So the number of moles, if I want, I can consider the number of moles. or the amount of the substance which has remained after 5% has been lost. So the new number of moles is going to be 0.95 times the original the number of moles which were there before, which is 150. And I think this is approximately 1. Okay, so this is giving, my calculator is giving me 142.5 moles. So that is the new amount of the substance. Now I can use PV is equal to nRT. So the pressure will be equal to nRT divided by the volume. Substituting, you have 142.5 times 8.31 times the temperature has remained 290 Kelvin divided by the volume. The volume is 1.8 times 10 power 4 times 10 power negative 6. So we can press the calculator. Okay, to two significant figures, my calculator gives me the new pressure as 1.9 times 10 power 7 pascals. Then the time t, now that one is also not very hard. So the number of the remember the amount has reduced by 5%. What is 5%? So the loss in amount of substance is 5%. That is 5 over 100 times 150. I think this is 5 times 15, that is 75. So this is 7.5 moles. So 7.5 moles are lost in a time t. 7.5 moles are the ones lost in a time t. And how many particles are these, or how many atoms, or how many nuclei are these? So that we can find the loss in the number of nuclei or the number of atoms. I will call this delta n, the change in the value of n. The change in the value of n is going to be equal to, remember, n is number of moles times Avogadro's number. So this will be the loss in the amount, which is 7.5 times Avogadro's number, which is 6.02 times 10 power 23. I'm just using n equals to number of moles times Avogadro's number. Remember that. So the loss, the number of nuclei which is lost, or number of particles lost, is number of moles lost times Avogadro's number. And we can press our calculator here. Okay, so this is giving me 4.52 times 10 power 24. But they have told us that the gas molecules leak from the container at a constant rate of 1.5 times 10 power 19 per second. That means in 1 second, 1.5 times 10 power 19 molecules are lost, or atoms, or molecules actually are lost. Then what time will it take to lose this number of molecules? So therefore, the time t is going to be equal to 4.52 times 10 power 24 divided by 1.5 times 10 power 19. So I press my calculator, just simply divide. This is giving me 3.0 times 10 power 5 seconds to two significant figures. Okay, so next, explain what is meant by the statement that two bodies are in thermal equilibrium. The statement that the two bodies are in thermal equilibrium. I think I explained this. Bodies are said to be in thermal equilibrium if they are the same temperature, meaning that there is no net energy transfer between the two bodies. So one, bodies are at the same temperature. Bodies are at the same temperature, and since they are at the same temperature, we say that there is no net energy transfer between them. We say there is heat flow in all directions at a constant rate, so the resultant thermal transfer becomes zero. Therefore, we simply say the bodies are the same temperature, and therefore there is no net thermal transfer, no net energy transfer between the bodies. Okay, our next question. Suggest suitable types of thermometers, one in each case, to measure the temperature of the flame of a Bunsen burner. Of course, the temperature of a Bunsen burner is relatively high. You cannot use the thermometers we use in the laboratory, the liquid in glass thermometer. You can't put it on a Bunsen flame. So this is a very high temperature, so we need a more suitable thermometer such as a thermocouple. Remember we said proper choice of the two different types of wires for thermocouple. The thermocouple can be used to measure a wide range of temperatures. The other one could be a pyrometer. A pyrometer can also measure a wide range of temperatures. We also have the platinum or the metal resistance thermometer. Platinum or the metal resistance thermometer. So those ones can measure such a wide range of temperatures. Then the change in temperature of a small crystal when it is exposed to a pulse of ultrasound. Of course, this is going to be a small change. There will be just a very small change in temperature. Therefore, we need an instrument which is extremely sensitive, such as a thermistor. A thermistor can measure such small change in temperature. A thermocouple can still measure such a small change in the temperature. Those are some of the thermometers that you can use to measure such small changes in temperature. Okay, next, some water is heated so that its temperature changes from 26.5 degrees Celsius to a final temperature of 38.0 degrees Celsius. State to an appropriate number of decimal places the change in temperature in the Kelvin scale. The change, we want the change. Here we just subtract. Remember, a change on the Kelvin scale is the same as a change on the centigrade scale, so I don't even need to waste time here. When we subtract here, the change in temperature on the Kelvin scale will be 38 minus 26.5. This is obviously 11.5 Kelvin. Do not make a mistake of again adding 273 on 11.5 Kelvin. If you want to verify, remember this one I just subtracted them when they're in degrees Celsius. Alternatively, you could add 38.0 plus 273.15 minus 26.5 plus 273.15. So we can check this again. 38 plus 273.15 minus 26.5 plus 273.15. So this one still gives you 11.5 Kelvin. Then the final temperature in Kelvin. The final temperature is 38. So we shall change this to Kelvin units. That is 38.0 plus 273.15. So this one is just checking that I can write the answer to an appropriate number of decimal places. So that is 38.0 plus 273.15. Note that if the temperature given is in decimal places, please use 273.15 rather than just 273. So this gives you 311.15, but I have tried this to an appropriate number of decimal places. So this becomes 311.2 Kelvin since the temperature is given to 2 decimal places. So I try to maintain the precision. Of the instrument used. Okay, next. A kettle is rated as 2.3 kilowatts, a mass of 750 grams of water at 20 degrees Celsius is poured into the kettle. When the kettle is switched on, it takes 2 minutes for the water to start boiling. In a further 7.0 minutes, half of the mass of the water is boiled away. So the change in mass is going to be, I think, 750 divided by 2. Okay, so estimate for this water the specific heat capacity. Estimate the specific heat capacity. Remember, for heat capacity, there is a change in temperature. So the amount of heat is equal to mc times change in temperature. The specific capacity will be, by the way, this is the same as power times time, the energy supplied to raise the temperature. So this would be 2300, that is the power, times the time, which is 2 minutes. So that is 2 times 60 to change it to seconds, divided by the mass and change in temperature. The mass here is 0.75, that is to raise its temperature. Then times the change in temperature is when it starts boiling, that is at 100, minus the original temperature, which is 20 degrees Celsius. The change in temperature on the Kelvin scale is the same as change in temperature on the degree Celsius scale. We can press our calculator. So this to two significant figures is 4,600 joules per kilogram per Kelvin. Then our estimate for this water, the specific latent heat of vaporization. So I have to look at it when it is vaporizing. That is, the time will be 7 minutes. The mass which has evaporated or vaporized is half. So the amount of heat supplied here will now be equal to the change in the mass times the latent heat of vaporization. So note that the latent heat of vaporization will now be equal to the heat supplied here, which is the energy supplied. This time the time has changed, is 7 minutes. So this will be, Q will be power, of course, still times time, divided by the mass which has vaporized. The power is 2300, but this time the time is 7 minutes times 60, divided by the change in the mass. The mass which has vaporized is half of 750, which is 375 grams. So this is times 10 power negative 3. We'll press the calculator. Pressing my calculator gives me L as 2.58 times 10 power 6. 2.58 times 10 power 6 as the specific latent heat of vaporization. So note that just doing these two questions, you get 5 marks. That is too much. Okay, next. State one assumption made in your calculations and explain whether this will lead to an overestimation or an underestimation of the value of the specific latent heat. State one assumption made. State one assumption made in your calculations and explain whether this will lead to an overestimation or underestimation of the value of the specific heat capacity. So which assumption have we made? We have made an assumption that there is no heat loss to the surrounding, but the truth is heat losses to the surrounding lead to an overestimation. So let's simply say that heat losses to the surrounding heat losses to the surrounding lead heat losses to the surrounding lead to an overestimation. That is one. Two, we have also not thought of condensation of water on the sides, which will also lead to an overestimation. Also, it is impossible for the power to be constant, so this also leads to an overestimation. So power is not constant. So this leads an overestimation. Power is not constant as we have assumed. Power cannot remain constant as we have assumed. So this could lead to an overestimation. I know some people may not easily know the spellings, so I have to be very careful. Alternatively, water condenses on the sides. Of the kettle. So this also leads to an overestimation. Okay. Next. The volume of some air assumed to be an ideal gas in the cylinder of a car engine is 540 centimeters cubed at a pressure of, so the volume is this at a pressure of 1.1 times 10 power 5 and a temperature of 27 degrees Celsius. I think that is 300 Kelvin. The air is suddenly compressed. That is, work is done on the gas, so that no thermal energy enters or leaves the system. That is, Q is equal to 0. No thermal energy enters or leaves the system. Q is equal to 0. And the volume is actually decreased to 30 centimeters cubed. The pressure rises to 6.5 times 10 power 6. Determine the temperature of the gas after the compression. So since they have told us the volume is changing, the temperature is changing, and the pressure is changing, so we shall simply say that PV over T is equal to a constant. So I will simply say that P1 V1 over T1 is the same as P2 V2 over T2. So I want to find the temperature T2. I will not convert the units of volume. I know they will cancel out. So I know that T2 is going to be P2 over P1 times V2 over V1, then multiplied by T1. That will be T2. I just made T2 the subject. For you can substitute if your algebra is not good. So we can now find T2 is going to be P2, which is 6.5 times 10 power 6 divided by 1.1 times 10 power 5. V2 is 30 centimeters cubed. V1 is 540 centimeters cubed. Then times T1. T1 is 27 degrees Celsius, which I think is 300 Kelvin, so times 300. So press our calculator, press your calculator too. So I am getting 984.8 Kelvin. Therefore, this is approximately 985 Kelvin. So that is adiabatic. By the way, if you knew this in details, adiabatic compression increases the temperature, and adiabatic expansion results to cooling. So this was a compression, no heat enters or leaves the system, so the temperature must increase. That is an adiabatic expansion, compression. State and explain the first law of thermodynamics. This is very easy. The first law states that delta U is equal to Q plus W. That is the change in internal energy. Change in internal energy. The change in internal energy is equal to heating of the system, or heat transfer to the system. Why am I poor in spellings? Heating of the system plus the work done on the system. So I have explained, I've stated the law and I've explained it. Delta U is a change in internal energy. If it is positive, of course, that would be an increase in internal energy. If Q is positive, that is heating of the system or heat transfer to the system. And plus, if W is positive, that is work done on the system. So I explained sign convention in one direction. Okay, next. Use the law to explain why the temperature of the air changed during the compression. Why the temperature of the air changed during the compression? You can go back to the first law of thermodynamics, delta U is equal to Q plus W. But there was no heat entering or leaving the system. That means no heat enters or leaves the system. That is Q is equal to 0. No heat enters or leaves. No heat enters or leaves the system. And if that is true, it means that the change in internal energy is only equal to the work done. So, change in internal energy equals to the work done. The change in internal energy will be equal to the work done. But then what is happening to the volume? The volume is decreasing. So since the volume decreases, work is done on the gas. Since volume decreases, work is done on the gas. In other words, the work done is positive. Positive work done means a positive internal energy is changing internal energy. So this means internal energy increases. So internal energy increases. And if internal energy increases, remember internal energy is equal to the total kinetic energy of the molecules. So it means total kinetic energy increases. And if the total kinetic energy of molecules increases, it means that the average kinetic energy also increases. So the average kinetic energy of molecules increases. And remember, temperature is the average kinetic energy of the molecules. So we simply conclude that thus temperature increases. So you can't fail to get 4 marks if you give an account which flows like that, because no heat enters or leaves the system. That is Q is equal to 0. So a change in internal energy is only depending on the work done. The change in internal energy is equal to simply the work done. And since it is the volume decreasing from 540 to 30 centimeters cubed, it means work is done on the gas. That is, work done is positive. So it means delta U is equal to positive Q, which means that the change in internal energy is also positive. So internal energy increases. And internal energy is equal to the total kinetic energy of the molecules for an ideal gas. So the total kinetic energy of molecules increases if the internal energy increases. And therefore, the average kinetic energy of the molecules also increases. Thus, we say that the temperature increases, because temperature is the average kinetic energy of these molecules. Okay, let's continue. The first law of thermodynamics can be represented by the expression delta U equals to Q plus W. State what is meant by the symbols in the expression. So the first one, the plus, the positive means an increase in internal energy, that is increase in internal energy. Then plus Q, the positive means heating of the system or heat energy added to the system, heat transfer to the system always. So this is heat energy, heating of the system, or it means heat transfer to the system, heat energy added to the system. Heat energy added to the system. Then positive W, that is work done on the system. Yeah, so that one, work done on the system. These ones we have already seen them. Okay, so next, in our next part, we have a fixed mass of an ideal gas undergoes a cycle that has been shown here, A, B, C, A. During the change from A to B, the energy supplied to the gas by heating is 442 joules. Use the first law of thermodynamics to show that the internal energy of the gas increases by 265 joules. So I have no space here, but I will still work out from here. First of all, from A to B, there is an increase in volume. So the work done is going to be negative. The gas is expanding. So work done will be equal to the pressure times change in volume, which is negative of, the pressure is 5 point, the pressure is 5 point, what is this scale? I think this is 5.2. Each small square is 0.2. So this will be 5.2 times 10 power 5 pascals, that is pressure, times the change in volume, We are moving from, I think this is 1.6. 1, 2, 3, 4, 5, 6, 7, 8 times 0.2. I think that is 1.6. And this one is, so this is 1.6. And this one is 5.0, I think. 1, 2, 3, 4, 5, 5.0. So the change in volume is 5.0 minus 1.6. The units, this is times 10 power negative 4. It is in SI units. When I press my calculator to find the work done, so this work done is negative 177 joules. That is the work done. So we want to find the change, the internal energy of the gas. The internal energy of the gas is given by Q plus work done. And Q is 440. It is supplied to the gas. So it is positive. This is positive. The other one is negative. So this will be equal to Q, which is positive 442 plus negative 177. When I get my calculator, 442 minus 177. This gives me the internal energy to be 265 joules. You can verify that. So the increase in internal energy is 265 joules. I hope the process is very easy. This one is heat supply to the gas, so it is positive. But when we look at the graph from A to B, the gas expands, meaning that the work done is negative. So the work done, we have obtained it as negative 177 joules. Therefore, we just substitute in the equation and we find our answer there. Okay, next. During the change from B to C, the internal energy of the gas is 313. B to C. Notice that B to C from the previous, from above, B to C, there is no change in volume. I hope people can see that. B to C, there is no change in volume. That means the work done is 0. So the change in internal energy is only dependent on B to C. The work done is 0 because there is no change in volume. Work done is pressure times change in volume. And since the change in volume is 0, it means the work done is also 0. By considering molecular energy, state and explain qualitatively the change, if any, in the temperature of the gas. First of all, you can just use a simple equation and see. The volume is constant. That means there's no change, there's no work done. And if there's no work done, it means there is no change, there is no potential energy, no molecular potential energy, no change in the molecular potential energy. But then, heat, the internal energy of the gas decreases by 313 joules. Since the internal energy decreases, and yet there is no work done, there is no molecular potential energy, it means the total molecular kinetic energy or the total kinetic energy of the molecules must be decreasing, which implies that the average kinetic energy of the molecules decreases, so the temperature must decrease. So change in internal energy is simply going to be depending on the amount of heat. But the internal energy decreases. And if the internal energy decreases, remember it is directly proportional to the kinetic energy of the molecules. So I'm saying since volume is constant, so that means there is no molecular potential energy. But no potential energy of molecules because it is going to depend on this work done. And since internal energy decreases, since the internal energy decreases, it means that the total kinetic energy of molecules decreases. So total molecular kinetic energy decreases because they are directly proportional. For an ideal gas, was it an ideal gas? Yes. Since volume is constant, no molecular potential energy. Since internal energy decreases, the total molecular kinetic energy decreases, implying that the average decreases. Implying that the average kinetic energy of the molecules decreases, so temperature decreases. I want you to master that temperature is the average kinetic energy of the molecules. In other words, temperature is directly proportional to the average kinetic energy of the molecules. And if the temperature decreases, then the average kinetic energy of the molecules also decreases. Okay, next. For the change from C to A, when you look at the stage C to A, let me take you back to C to A. C to A, you notice that the volume is decreasing from 5 to 1.6 as the pressure is increasing. Volume is decreasing, pressure is increasing. Volume is decreasing, pressure is increasing. Okay, so they're asking us to calculate the change in internal energy from C to A. For the change from C to A, use the data in B Roman 1 and B Roman 2 to calculate the change in internal energy. The change in internal energy. So we want the change in internal energy from C to A. If we start from A, move to B, C back to A, it means the total change in internal energy is going to be 0. So that is the change in internal energy along A to B plus the change in internal energy along B to C plus the change in internal energy from C to A. The change in internal energy from C to A, this should be equal to 0 because when we come back to the A to point A, we have come back to the original temperature. And so we want to find the change in internal energy from C to A. The change in internal energy from C to A. This will be equal to the change in, plus the change in internal energy from A to B, the change in internal energy from A to B. A to B, A to B, A to B. I think we have got, they told us that from B to C, the internal energy of the gas decreases by, okay, let me begin with B to C. It decreases by 313 from B to, so this will be negative 313 because it decreases. Then from A to B, I think they told us internal energy of the gas increases by 265 from A to B. During the change from A to B, during the change from A to B, during the change from A to B, the internal energy increases. This one, it increases, so it will be positive. So this will be positive 265, and this should give us 0. So that means the change in internal energy from C to A is going to be 313 minus 265, and this is going to give us the difference, which is 48 joules. So that is the change in internal energy. I can just bring it here for completeness. So the total change in internal energy should be 0. So the change in internal energy that we want, that is from C to A, when I add it to the change from A to B, where they said from A to B the change was 265 positive, so that would be 265 joules, plus from B to C, which was a decrease, that was negative 313, the total change should be 0. That means when you simplify this, you know that the change from C to A is going to be 313 minus 265, which gives us 48. And then next, the temperature of the gas at point A is 227 degrees Celsius. Calculate the number of molecules in the fixed mass of the gas. Number of molecules, that is easy. PV is equal to nRT. And we know that number of molecules is equal to the number of moles times Avogadro's number. So I can simply substitute here. Okay, so this means PV is equal to N over Na times R times T. So I can find N as PVNA divided by RT, or I would have substituted R over Na with K. So the pressure is 5.2 times 10 power 5. And we have already seen that the volume was 1.6 times 10 power negative 4. Divided by, we are at point A, remember. R is, of course, 8.3 times 8.31, that is R. Then T, we have T is 227, which is 227 plus 227 plus 273. This is 500. Then times Avogadro's number, which is 6.02 times 10 power 23. When I press my calculator here, so this is giving me 1.2 times 10 power 22. Okay, just a moment. Okay, so the number of molecules is 1.2 times 10 power 10. 1.2 times 10 power 10, times 10 power 22. That is the number of molecules. Okay, we can continue, we can proceed. A cylinder contains 5.12 moles of unidentified gas at a pressure of that and the volume of this. Determine the temperature of the gas. Determine the temperature of the gas. So I will just use PV is equal to nRT. I make T the subject. So T will be equal to PV over nR. So I'm substituting. Volume is pressure is 5.60 times 10 power 5 times the volume, which is 3.80 times 10 power 4 times, I change it to meters cubed, times 10 power negative 6, divided by number of moles is 5.12, molar gas constant is 8.31. When we substitute, press the calculator. 5.6 exponent 5 times 3.8 exponent negative 2 divided by 5.12 divided by 8.31. So I'm getting 500.2, which is approximately unavoidable. It is unavoidable to write 500 Kelvin. Okay. The average kinetic energy, EK, of a molecule is given by that expression. K is Boltzmann's constant. Use your answer in A to determine the new volume of the gas. The gas is heated at a constant pressure so that the temperature rises by. So that is the change in temperature. The temperature rises by that. Use your answer in A to determine the new volume of the gas. Okay? Determining the new volume of the gas. Because the pressure is constant, then the volume is directly proportional to temperature. So I will say V1 over T1 should be equal to V2 over T2 because the pressure is constant. So V2 is going to be equal to V1 over T1 times T2, where V1 is, what is V1? Our volume initially was 3.80 times 10 power negative. It was, okay, I can maintain it in meters, centimeters cubed, so times 10 power 4. Then times T1, oh sorry, times T2, I'm cross multiplying, times T2, remember the temperature increases by 125, so T2 is going to be the initial temperature, which was, what was the initial temperature? The initial temperature, we have calculated 500, so this will be 500 plus 125, that is the new temperature T2, divided by the temperature T1, which is actually 500. Alternatively, you can substitute directly in this expression here. I'm pressing my calculator. So this is 4.75 times 10 power 4 centimeters cubed. Then next, calculate the increase in internal energy of the gas. Explain your working. Increase in internal energy of the gas. I think the gas is ideal, so it means the change in internal energy is simply directly proportional to the total kinetic energy of the molecules. So for an ideal gas, the change in internal energy or the increase in internal energy will be equal to the change in the total kinetic energy of the molecules. So this will be equal to the change in total kinetic energy of the molecules. And if that is true, we already know from above that the average kinetic energy of just one molecule is that. So the total kinetic energy of all the molecules will be the average of one molecule times the number of molecules. But also remember, okay, so the change in internal energy will be equal to, for one molecule, that will be 3 over 2 times kT. That is for one molecule, then times the number of molecules. But remember, number of molecules is number of moles times Avogadro's number. So this will be 3 over 2 times kT times the number of moles times Avogadro's number. I think this is enough for me to substitute. So this will be 3 over 2 times 1.38 times 10 power negative 23, that is K. Then the temperature, of course, there has been a temperature change here. So I will say this is change in temperature because the change in internal energy should be directly proportional to the change in total kinetic energy, which is directly proportional to the change in temperature, delta T. So the change in temperature is given as 125 Kelvin. So this is times 125. Number of moles, we have already been given 5.12 moles times Avogadro's number, which is 6.02 times 10 power 23. We now press the calculator. Oh, I've written this very poorly, very, very poorly. So this is 3 over 2. Okay, when I press here, so pressing my calculator is giving me 7,980 joules. 7,980 joules. This means we can continue. So the increase in internal energy is approximately 7,980 joules to 3 significant figures. They said explain your working. That's why I said for an ideal gas, the change in internal energy is equal to the change in the total kinetic energy of all the molecules. Use your answer in B Roman 1 to determine the external work done during the expansion of the gas. Work done during the expansion of the gas, we know that work done is pressure times change in volume. Pressure times change in volume. So the work done is the pressure, which is 5.60 times 10 power 5 pascals. The volume changed from 3.8 to 4.75 as we have calculated above. So I will say 4.75 minus 3.80, then times 10 power 4, that was the power of 10, that is in centimeters cubed. So I say times 10 power negative 6 to change it to meters cubed. So we can now press the calculators. 4.75. So from my calculator, I have work done as 5,320 joules. Calculate the total thermal energy required to heat the gas in B. Total thermal energy required to heat the gas in B. Okay, so the change in internal energy is equal to the thermal energy plus the work done, heating of the system plus the work done. But then the work done, determine the external work done during the expansion of the gas. The gas is expanding, so the work done is negative. And this was an increase in internal energy. An increase in internal energy is positive. So we are just substituting. So this will be 7,980 equaling to Q plus the work done should be negative 5,320 because the gas was expanding. So the work done is negative. So when I substitute or when I simplify, then this gives me Q. The value of Q is actually going to be equal to 7,980 plus 5,320. And when you press your calculator to add this 7,980 plus 5,320, I'm getting 13,300. So that is the total thermal energy required to heat the gas. Okay, so we can continue. Use one of the assumptions of the kinetic theory of the gas to explain why the potential energy of the molecules of an ideal gas is zero. One of the assumptions, that is the one which deals with the force. So we simply say no intermolecular forces. No intermolecular forces. There are no intermolecular forces. So the potential energy is negligible. Also no potential energy, or the potential energy is negligible. No intermolecular forces, so no potential energy, or the potential energy is negligible. Okay. The average translational kinetic energy of a molecule of an ideal gas is given by this expression here. Okay, so state the meaning of the symbol. This one is the mean square speed of molecules. Mean square speed of molecules. Mean square speed of molecules, or the average square speed of molecules. Then it is the Kelvin temperature, or the absolute temperature, or temperature in Kelvin units. Temperature in Kelvin units, or the absolute temperature, or the thermodynamic temperature. Then a cylinder of constant volume 4.7 exponent 4 centimeters cubed contains an ideal gas at this pressure here and this temperature. The gas is heated. The thermal energy transferred to the gas is 2,900 joules. It is transferred to the gas, so most likely it is positive. The final temperature and pressure of the gas are T and P as illustrated. Calculate the number of molecules in the gas, in the cylinder. So PV is equal to N times RT. Remember, N is number of molecules divided by Avogadro's number, then times RT. I think this is even enough for us to find number of molecules, but I can still remove R over NA so that it becomes NKT, because R over Na is Boltzmann's constant. So the number of molecules is going to be PV divided by K times T. So this will be P is 4.7 times 10 power 4 in centimeters cubed times 10 power negative 6 to change it to meters cubed times, so that was volume. Then pressure 2.6 times 10 power 5 divided by K is 1.38 times 10 power negative 23. The temperature is 173 when you change it to Kelvin, so this is plus 273, and I think that is 446. So this is times 446. Pressing the calculator, N is going to be equal to 2.0 times 10 power 24. So that is the number of molecules. Then calculate the increase in the average kinetic energy of the molecules during the heating process. So note that when you look at the illustration, the volume has not changed. That means the work done is 0. So since the volume is constant, so I will say no change in volume is equal to 0, meaning that the work done is equal to 0. So the increase in internal energy is simply equal to Q, because the work done is 0. And remember, the total kinetic energy of the molecules is directly proportional to the change in internal energy. The total kinetic energy of the molecules is directly proportional to the change in internal energy. So it means the change in internal energy is going to be equal to Q, which Q is given as 2,900 joules. But we want the average. So it means the average increase in internal energy will be equal to the average kinetic energy. So the average increase will simply be 2,900 divided by the number of molecules. This is be 2.0 times 10 power 24. So I can press my calculator. So this is giving me 1.5 times 10 power negative 21. Remember I said the change in volume is 0, so there is no work done. Using the first law of thermodynamics, W will be 0, so the change in internal energy is just equal to Q. So the change in internal energy is simply equal to the heat supplied. But remember, internal energy is equal to the total kinetic energy of the molecules. Now, if I want the average, it means I have to divide by the number of molecules. So that's why I've divided by the number of molecules in the cylinder. Okay? Use your answer in Roman 1 part 2 to determine the final temperature T in Kelvin of the gas in the cylinder. So we are using the answer in Roman 1 part 2, which is the average kinetic energy of the molecules. But we know the formula. We know that the average kinetic energy of the molecules is equal to 3 over 2 times kT. So the change, the average kinetic energy of the molecules will be equal to the change 3 over 2 K times the change in temperature. So we shall say 1.5 times 10 power negative 21 is going to be equal to 3 over 2 times K, which is Boltzmann's constant, 1.38 times 10 power negative 23. So this is times 10 power, so this will be times 10 power negative 23. Then we multiply this by the change in temperature. So when I press my calculator, the change in temperature is going to be equal to making the change in temperature the subject times 2 divided by 3. So the change in temperature from my calculator is 72.5 Kelvin. That is the change in temperature, but we want the final temperature. So the final temperature T will be equal to the initial temperature in Kelvin, which was 173 plus 273 to change it to Kelvin. That was the initial temperature plus the change, which is 72.5 to get the final temperature. And this is approximately 5. This is okay. This is 6. Okay, so that is approximately 520 Kelvin. So that is the change in temperature. Okay, next. During melting, a solid becomes liquid with little or no change in volume. Use the kinetic theory to explain why during the melting process, thermal energy is required although there is no change in temperature. Why is thermal energy required even though there is no change in temperature? So earlier on we saw that the heat supplied may not go into increasing the kinetic energy of the molecules, but during melting, the heat supplied goes into breaking the bonds between the molecules. The potential energy of the molecules is the one which is increased, but not the kinetic energy of the molecules. So we say that no or little work is done, so thermal energy input is actually required to break the bonds. So during melting, heat is supplied. During melting, heat is supplied. So during melting, the heat supplied goes into breaking the bonds. It goes into breaking the bonds between molecules. The heat supplied goes into breaking the bonds between the molecules or between the atoms. So it is the potential energy which is increased. So potential energy of molecules is increased slightly, but not the kinetic energy of the molecules. So the potential energy of the molecules is the one which is increased, but not the kinetic energy of the molecules. So the temperature does not change. Little work is done, or no or little work is done. Some thermal energy input is going to be required. Since little work since no or little work is done, thermal energy input is required. So since some little work is done, let me just be on the positive side. Since some little work is done, thermal energy input is required. Thermal energy input is required. And this is the latent heat. So that will be the latent heat, which will be required to break those bonds. Okay, next. An aluminium can of mass 160 grams contains a mass of 330 grams of warm water at a temperature of 38 degrees Celsius. A mass of 48 grams of ice at 18 degrees Celsius is taken from a freezer and put into the water. The ice melts, and the final temperature of the can and its contents is 23 degrees Celsius. Data for the specific capacity of aluminium, ice, and water are given in the table. Assuming no exchange of thermal energy with the surrounding, which is a wrong assumption, show that the loss in thermal energy of the can and the warm water is 2.3 times 10 power 4 joules. So, the loss in thermal energy, where does the thermal energy of the can and the warm water go? So this will go into raising the temperature of the water and of course raising the temperature of, show that the loss in thermal energy of the can and the warm water is going to be that. So this is going to go into raising the temperature of the water will change and the temperature of the can will also change. Therefore, we shall say that the loss in the thermal energy is going to be equal to that which is lost by the water, that is mc delta theta time for water, plus that which is lost by the can, I will say mc delta theta for the can. So this is the loss, the total loss in the thermal energy. So the loss is going to be equal to, because there will be a change in temperature, the mass of the water is 160 times the specific capacity of water is 0.910. No, that is not for the water. This is for the can. This is for the can. For the water, okay, let's begin with the can. There is no problem. The mass of the can is 160. The specific capacity of the can from the table is 0.910. I've not changed the units from grams to another unit because I know they will cancel out. This is joules per gram, the other one is grams, so they cancel out. Then times the change in temperature. For the can, its initial temperature is, let me check. Warm water at a temperature of this. So the initial temperature for both is 38 and the final temperature is 23. So the temperature change for both is 15. So this is 38 minus 23 plus this was for the can. Now for the water, the mass of the water is 330. Specific capacity is 4.18. I will not change the units. The change in temperature is 38 minus 23. When I press my calculator, so my calculator is giving me actually exactly 2.3 to two significant figures, 2.3 times 10 power 4 joules. 2.3 times 10 power 4 joules as required. Use the information in Roman 1 to calculate a value for the latent heat of the specific latent heat of fusion of ice. So, the heat lost by the water and the can, where does it go? This should be increasing. It will first of all melt the ice. But before the ice, of course, the ice is at negative 18 degrees. So its temperature must raise from negative 18 degrees to to 0 degrees Celsius, then it starts melting, and again the temperature rises from 0 to 23. So we shall say qualitatively that the loss in heat, one, it goes into heating. It is going to be the heat which increases ice temperature or temperature of the ice temperature from negative 18 degrees Celsius to 0 degrees Celsius. Then after it has reached 0 degrees Celsius, now it melts. That is heat which goes into melting the ice. That is at 0 degrees Celsius. When all the ice has melted, now its temperature rises from 0 to the final equilibrium temperature, which is 23. So plus the heat which goes into increasing the temperature of melted ice, from 0 degrees Celsius up to 23 degrees Celsius. So that is now very easy. So we shall say that 2.3 times 10 power 4 is going to be equal to the heat which goes, remember when there's a rise in temperature, a change in temperature, we use mc delta theta. When there is a change of state, we use m times the latent heat. So this one, remember when there is a change in temperature, we use mc times the change in temperature. When there is no change in temperature, we use m times the latent heat. So for the first case, there is a change in temperature, so I'll use m. So this is 48, that was the mass, times this is going to be 2.10 for ice, then times the change in temperature, which is from negative 18 to 0 degrees Celsius, that is 0 minus 18. So this will be 18. That is a change in temperature. Plus, now here there is no change in temperature, so we use the latent heat. So this will be mass of ice, 48, times the latent heat. Then plus, again there is a change in temperature, so the melted ice has a mass of 48 times, of course, now that it is melted, its specific capacity is that of the water, which is approximately 4.18, times the change in temperature is from 0 to 23, so the change is 23. So note that I have not converted the mass to kilograms because I know the specific capacity units, always cancel them out. So this means I now have that 48 times latent heat is going to be, let me simplify this. So this is 1.66 times 10 power 4. Then when I try to find L, just simply divide. So this is giving me approximately 350 joules per gram. So the specific latent heat of fusion of ice is approximately 350 joules per gram. I think the most common value is 330 joules per gram. Okay, next. State what is meant by internal energy of a system. State what is meant by internal energy of a system. I think this is now a more familiar question. The sum of the random distribution of the kinetic and the potential energies of all the molecules that make up the system. The sum of the random distribution of the kinetic energy and the potential energy of all the molecules or particles, or molecules, particles, or atoms that make up the system. The sum of the random distribution of the kinetic and potential the sum of the random distribution of the kinetic and the potential energies. Why can't it erase? The sum of the random distribution of the kinetic energy and the potential energy of all the molecules that make up the system. That is internal energy of the system. Explain why for an ideal gas the change in internal energy is directly proportional to the change in thermodynamic temperature for an ideal gas. So first of all, we know for an ideal gas, no intermolecular forces, so no potential energy. That is the starting point. For an ideal gas, we have no intermolecular forces, so there's no potential energy. Internal energy, remember, is the sum of the random distribution of the kinetic energy and potential energy of all the molecules that make up the system. Now that there is no potential energy, it means internal energy is solely kinetic energy of the particles, or is now depending only on the kinetic energy of the particles. So I will say internal energy is solely or only kinetic energy of the particles, is only the kinetic energy of the particles, or is only depending on the kinetic energy of the particles. A change in internal energy means a change in total kinetic energy. Change in internal energy means a change in total kinetic energy of the molecules. Change in internal energy means a change in total kinetic energy of the molecules, which also implies a change in the average kinetic energy of the molecules, which is directly proportional to the change in the average kinetic energy of the molecules. And remember, temperature is directly proportional to the average kinetic energy of the molecules. So this is, I'll just say, which is proportional to the average, which is proportional to the temperature. So this is proportion to the temperature of the gas. Okay, so I think that will be enough to give you 3 marks. A cylinder of volume 1.8 times 10 power 4 contains a gas at this pressure and at this temperature. So you remember to change the temperature to Kelvin units. Helium gas may be considered to be an ideal gas consisting of single atoms. Calculate the number of helium atoms in the cylinder. Number of helium atoms. So we know that from PV is equal to nRT. Number of moles is number of molecules divided by Avogadro's number times R times T. If I want to remove R over Na, I can introduce K. So this becomes NKT. So number of molecules, number of helium atoms will be PV divided by K times T. Simple substitution, this will be 6.4 times 10 power 6 times the volume, which is 1.8 times 10 power 4. I may change it to meters cubed, that is times 10 power negative 6, divided by K is Boltzmann's constant, 1.38 times 10 power negative 23. The temperature is 25 degrees Celsius. In Kelvin, this is 298. I guess that is 298 Kelvin. And when you press your calculator, pressing my calculator, this gives me 2.8 times 10 power 25. 2.8 times 10 power 25. Okay, next, state the basic assumptions of the theory of the kinetic theory of gases that leads to conclusion that the potential energy between the atoms of an ideal gas is zero. That one is now a common question. No forces of attraction or repulsion between the atoms, or the intermolecular forces are negligible. Intermolecular forces are negligible. Intermolecular forces are negligible. There are no forces of repulsion or attraction between the molecules or even between the atoms. Intermolecular forces are negligible. No forces of attraction between the molecules or forces of attraction or repulsion between the molecules. So we simply say intermolecular forces are negligible. State what is meant by internal energy of a system. You'll get tired of that question several times, but this is good to make you confident. The sum of the random distribution. The sum of the random distribution of the kinetic energy and potential energy of all the molecules that make up a system, or making up a substance, of all the molecules of a substance. So that is the internal energy of a substance. Next, explain why an increase in internal energy of an ideal gas is directly related to the rise in the temperature. Remember, internal energy is equal to Ek plus E potential. And the potential component is zero because for an ideal gas, the intermolecular forces are negligible. So we say there is no potential energy no potential energy for an ideal gas. So kinetic energy of the molecules increases with the temperature. There is no potential energy. The kinetic energy of molecules increases with the temperature because temperature is the average kinetic energy of the molecules. So kinetic energy of molecules increases with the temperature. And if the kinetic energy of molecules increases, it also means the internal energy increases. So increase in temperature increases internal energy. So the other way around is what we have considered. Because the potential energy component is zero, there is no potential energy. It is only the kinetic energy contributing to internal energy. The kinetic energy of molecules, we know it increases when the temperature increases. And if that is true, if temperature increases, then the internal energy should be increasing because they are directly proportional. They are directly proportional.